There is a profound and unsettling quiet that blankets the cosmos, a silence so deep and vast it seems to swallow sound itself. Out beyond the gentle glow of our familiar planets, past the last vestiges of our sun's warm light, lies an infinite expanse of pure, unbroken black. It is a darkness that is not merely the absence of light, but an active, almost sentient void, hiding realities so bizarre and forces so immense they defy everything we think we know. We gaze up at the star-dusted night sky and see beauty, but we are only looking at the cover of a book whose pages are written in the language of cosmic terror. This is the true nature of deep space, not a peaceful emptiness, but a realm of ancient, indifferent power, where the laws of physics twist into nightmares and light itself can be torn apart. It is a frontier that calls to our deepest curiosity, yet whispers a warning of things we are only just beginning to comprehend. We are about to embark on a countdown through the top 25 scariest things in deep space, a journey that will take us to the very edge of understanding and perhaps a little bit beyond. We will confront entities and phenomena that are not just strange, but actively hostile to life as we know it. From the silent, gravitational grip of dark matter that binds the universe together unseen, to the screaming voids where galaxies refuse to form, the cosmos is filled with wonders that are equal parts magnificent and terrifying. This is not a tour of pleasant astronomical curiosities. This is an expedition into the heart of cosmic dread, where we will meet monsters born from the fabric of space-time itself. So prepare yourself for a voyage into the unknown, a descent into a reality far stranger and more frightening than any fiction. What you are about to witness will challenge your perception of the universe and send a genuine shiver down your spine as we peel back the layers of the night to reveal the terrifying truths waiting in the dark. And now we arrive at our first entry, a predator that embodies the silent, drifting terror of the void, the rogue black hole. Picture the most perfect camouflage imaginable, not the stripes of a tiger or the colors of an octopus, but the utter blackness of gravity itself. These are not the stationary monsters anchored at the centers of galaxies, around which stars dutifully orbit. No, these are the nomads, the drifters, the ghosts of the cosmos. They are invisible, detectable only by the subtle way they warp the light of stars behind them, or by the frantic, doomed dance of a star suddenly caught in an unseen gravitational grip. Their formation is a story of cosmic violence, born from the most colossal collisions imaginable. When two galaxies slam into each other in a slow-motion ballet of destruction, the supermassive black holes at their hearts can be flung outward, ejected from their home galaxies by immense gravitational forces. They are cast adrift, set on a random, unstoppable course through the interstellar dark with nothing to announce their coming but the faintest ripple in space-time. To understand the threat, consider our own solar system as a perfectly balanced mobile, each planet hanging from its string, orbiting in a precise, delicate dance around our sun. Now imagine an invisible, heavyweight fist slowly pushing its way into that mobile. A rogue black hole wouldn't even need to make a direct hit to spell our doom. As it silently glides through the outer reaches of our system, its immense gravity would act like a cosmic spoiler, disrupting the fragile orbital harmony that has persisted for billions of years. The outer planets would be the first to feel its pull, their orbits stretching into wild, elongated ovals, sending them careening into new paths that would inevitably cross the inner solar system. A gravitational tug from this unseen passerby could send Neptune or Uranus on a collision course with Jupiter, or fling Mars hurtling toward Earth. The familiar clockwork of our celestial neighborhood would be shattered into chaos. But the true, visceral horror comes if one were to pass closer. There would be no dramatic impact, no fiery explosion from a collision. The destruction would be far more insidious and absolute. The black hole's gravity would begin to pull our planet apart long before it was consumed. the side of Earth facing the black hole would feel a significantly stronger pull than the far side, stretching our entire world. The solid ground beneath our feet would begin to quake and fracture on a global scale, the very rock and metal of our planet torn by a force greater than its own gravity. Our atmosphere would be ripped away, our oceans boiled off into space, and the planet itself would be shredded into a stream of incandescent debris, spiraling silently into the ultimate nothingness. The sun would simply vanish from the sky, not in a sunset, but blotted out by an absence, a patch of perfect black that grows until it is all that remains. The scariest part is the silence and the stealth. A giant asteroid we might see coming for years or decades, a nearby supernova would bathe our sky in impossible light for weeks. But a rogue black hole offers no such warning. It is the perfect hunter drifting on a billion-year journey, its path random, its arrival unannounced, and its passage leaving behind only the cold, empty silence of a star system that has been permanently erased. The terrifying truth about these dark wanderers is that by the time we could detect one with any certainty, it might already be too late. Our primary method for finding black holes involves watching for the high-energy radiation blasted out as they actively consume matter. But a rogue black hole traveling through the emptiness between stars is a fasting predator, its plate clean, emitting nothing. It is only through its subtle warping of space-time, an effect called gravitational lensing, that we might get a fleeting warning. This would manifest as a temporary, strange brightening and distortion of a distant star, a celestial mirage that appears, shifts, and then vanishes as the black hole moves on its path. But such events are incredibly rare and difficult to distinguish from other astronomical phenomena. The first sign for our solar system might not be a visual one at all, but a gravitational tremor. We would notice it in the skies long before we felt it on the ground. The outer solar system, a realm we often think of as stable and predictable, would begin to behave strangely. The delicate gravitational balance that has held for eons would be perturbed by this new, unseen mass. A planet like Neptune or Uranus might begin to drift from its calculated path, its orbit becoming slightly irregular. At first, astronomers would puzzle over the data, checking and rechecking their instruments, suspecting an error in calculation or an undiscovered planet. But as the intruder drew closer, the anomalies would become undeniable chaos. The real danger lies in the sheer power of its gravity to not just capture but to catapult. One of the most fearsome abilities of a rogue black hole is what scientists call a gravitational slingshot. This isn't a gentle nudge, it's a violent, unpredictable launch. As a planet swings around the black hole, it could be accelerated to speeds that allow it to break free from the sun's gravity entirely, becoming a rogue planet itself, ejected into the eternal cold of interstellar space. Conversely, another world could be flung inward onto a collision course with the inner planets, turning a once stable neighbor into a celestial bullet. The entire architecture of our solar system, a structure that has nurtured life for billions of years, could be dismantled in a cosmic game of pinball with Earth as one of the balls. And if a star were to stray too close to one of these dark nomads, the result is one of the most violent events in the universe. The black hole's tidal forces, the difference in gravity between the side of the star nearest the hole and the side farthest away would stretch and squeeze the star enormously. It would be spaghettified, pulled into a long, thin stream of superheated plasma before being devoured, lighting up the void with its death throes in a brilliant but tragic flare. This very process is what astronomers are now desperately trying to use to hunt these ghosts. Projects like the Laser Interferometer Gravitational Wave Observatory, or LIGO, listen for the faint ripples in space-time caused by colossal events, including black hole mergers. By building a census of where black holes are and how they move, we hope to one day predict their paths. Other efforts involve continuously monitoring millions of stars, looking for those telltale, fleeting moments of gravitational lensing that betray an invisible object's passage. It is a cosmic search for footprints in the dark, an effort to map the movements of the ultimate predators so that we might, perhaps, have just enough warning to understand our fate, even if we are powerless to change it. Moving from the silent, drifting menace of rogue black holes, we encounter a threat defined by its blinding, instantaneous violence. If a rogue black hole is a stealthy assassin, then a gamma-ray burst is the universe firing a cannon in our direction. These are not mere explosions, they are the single most powerful release of energy the cosmos has yet conceived. In the span of a few seconds, a single gamma-ray burst can outshine every star in 100 billion galaxies combined. That raw, unfathomable power is focused into two narrow, opposing jets of the highest energy radiation in existence, and if one of those jets were to be pointed at Earth, the consequences would be swift and absolute. The genesis of such an apocalyptic event typically lies in the death of a particular kind of star, a massive, rapidly spinning wolf in sheep's clothing. As this star exhausts its nuclear fuel, its core collapses not into a quiet stellar ember, but into a newborn black hole. In that fraction of a second, vast amounts of matter swirl into the abyss at near light speed, and through processes we are still striving to understand, this chaotic maelstrom funnels a colossal amount of energy into two narrow beams that scream across the universe. Another type arises from the collision of two super-dense stellar corpses like neutron stars, merging in a titanic embrace that also births a black hole and for a fleeting moment unleashes a similar torrent of gamma rays. These beams are the ultimate cosmic blowtorches, and their danger lies not in heat or kinetic impact but in pure, penetrating radiation. To understand the effect on a planet like ours, we need to look not at the sky, but at our own fragile shield, the ozone layer. This thin, invisible blanket of gas in our upper atmosphere is all that stands between life on the surface and the sun's harmful ultraviolet radiation. A gamma-ray burst striking our planet would not scorch the surface directly. Its photons are too energetic for that. Instead, the real devastation happens in the air above us. The gamma rays would smash into the molecules of our atmosphere, ripping nitrogen and oxygen atoms apart with violent efficiency. These shattered atoms would then recombine into nitric oxide and other nitrogen oxides, which act as a catalyst to destroy ozone. In a terrifyingly short time, a significant portion of our planet's protective ozone layer could be obliterated. The aftermath is a scenario of quiet, creeping death. With our shield gone, the sun's full, unfiltered ultraviolet radiation would bathe the planet's surface. Land-based life would suffer catastrophic radiation burns. The base of the marine food web, the phytoplankton that produce over half of our planet's oxygen and form the foundation of the ocean's ecosystem, would be devastated. A global extinction event would unfold not from fire and brimstone, but from a silent, invisible onslaught that attacks the very fabric of the ecosystem. The fossil record itself may hold a ghostly fingerprint of such an event. One of the major extinction events in Earth's deep past, the Ordovician Silurian extinction around 440 million years ago, wiped out a massive percentage of marine life. The pattern of die-off is peculiar. It disproportionately affected shallow water organisms that would have been most exposed to heightened UV radiation, while deeper sea life was relatively spared. Some scientists have proposed that a relatively nearby gamma-ray burst could explain this strange selectivity, a theory that transforms an ancient biological mystery into a potential warning from our own planet's history. The probability of a gamma-ray burst occurring in our galactic neighborhood and being aimed precisely at us is thankfully exceptionally low. Most of these events we detect come from galaxies billions of light-years away, far enough that their lethal jets pose no threat. The true terror lies in the combination of absolute power and unpredictable timing. Unlike an asteroid impact we might one day deflect, there is no defense against a gamma-ray burst. There is no bunker deep enough, no technology that could shield an entire hemisphere of a planet from such an atmospheric catastrophe. If one were to occur within a few thousand light years and Earth found itself in the crosshairs, the only warning we might receive would be a brief, brilliant flash in the detectors of a few satellites, a final, fleeting message before the slow, biological collapse began. Leaving behind the apocalyptic flash of gamma-ray bursts, we confront a different kind of terror, one that operates not in a blinding instant, but with the slow, inexorable pull of a cosmic tide. This brings us to a mystery that lies in our own galactic backyard, a gravitational puzzle known as the Great Attractor. For decades, astronomers mapping the grand flow of galaxies through the universe noticed something profoundly unsettling. Our own Milky Way, along with our entire local group of galaxies and thousands of others, is not moving randomly. We are all caught in a vast river of stars, streaming at a staggering 2 million miles per hour toward a specific point in the darkness behind the constellation Centaurus. Something with the mass of tens of thousands of Milky Way galaxies is pulling us, a cosmic puppeteer whose strings are woven from gravity itself. The sheer scale of this motion is humbling. It speaks of a force so immense that it can orchestrate the movement of entire galactic superclusters, guiding them on a course set billions of years ago. This isn't a future collision in the traditional sense, but a relentless drift toward a gravitational center we cannot see, a destination that remains hidden behind a cosmic curtain. The fear it evokes is not of a sudden impact, but of the unknown. We are being pulled toward a shadow in the universe, a place that by all rights should be one of the most brilliant concentrations of light in the sky, yet it is veiled from our sight. This is the core of the horror. We are caught in a flow we do not understand, heading toward a destination we cannot see. This unsettling reality is compounded by a simple but profound observational handicap: our own galaxy gets in the way. The plane of the Milky Way is thick with cosmic dust, gas, and a dense swarm of stars, creating a region astronomers call the zone of avoidance. From our vantage point inside this stellar disk, looking toward the center of the Great Attractor is like trying to see a distant mountain range through a dense, perpetual fog bank. This obscuration has turned the heart of this immense gravitational anomaly into a blind spot in our map of the cosmos. A blank space that, for a long time, fueled speculation about what monstrous structure could possibly be lurking there. Early theories born from this lack of data were naturally dramatic. Could it be a single, unfathomably massive object, a gravity well of such density that it defied known physics? Or perhaps it was something even more exotic, a cosmic defect in the fabric of space-time, a knot left over from the Big Bang that was now gathering matter around it. The inability to see what was there allowed the imagination to run wild, painting pictures of ancient, terrifying entities hidden in the galactic glare. The true nature of the Great Attractor began to come into focus not with optical telescopes, but with instruments that could peer through the cosmic fog. Astronomers turned to radio, infrared, and X-ray observatories, wavelengths of light that can penetrate the dust clouds that block our visible light view. What they found was both less sinister and, in its own way, even more awe-inspiring. The Great Attractor is not a single, monstrous entity, but rather a gravitational focal point, the core of a colossal supercluster of galaxies now known as the Laniakea supercluster. Laniakea, a Hawaiian word meaning immense heaven, is our true cosmic address, a vast filament of over 100,000 galaxies spanning 500 million light-years, all bound together by gravity and flowing toward a common center of mass. Our Milky Way is merely a suburb in this sprawling metropolitan expanse of the universe. The pull we feel is the collective gravity of this immense structure, with its greatest density lying in the direction of the Norma cluster, a massive gathering of galaxies located near the core of the Great Attractor. So, the mystery is partially solved. We are not being pulled toward a single hidden monster, but toward the heart of our own cosmic continent. Yet, the story does not end there. Even accounting for the mass of the entire Laniakea supercluster, the math still doesn't perfectly add up. The observed motion of our galaxy and its neighbors is still slightly too fast, suggesting there is an even larger source of gravity at work pulling on Laniakea itself. This points to something beyond, an even more immense structure, perhaps the titanic Shapley supercluster, located even farther away, acting as the next great gravitational anchor in the cosmic web. This realization deepens the existential unease. The great attractor is not the final destination, but merely a waypoint in a much grander, more terrifying flow. We are like a leaf caught in a river, pulled by the local current toward a lake, only to discover that the entire lake is itself flowing toward a vast, distant ocean. Our fate is not tied to a single point in space, but to the relentless, hierarchical pull of the universe's large-scale structure, a gravitational cascade that operates on scales so vast they defy human intuition. The fear evolves from worrying about what specific monster lies in the dark to a profound unease about our place in a cosmos where even the mightiest superclusters are just pawns in a game whose rules are written on the fabric of spacetime itself. But as profound as the gravitational pull of the great attractor may be, it operates within the known laws of physics. Our next entry, however, threatens the laws themselves. This is the concept of vacuum decay, a hypothesis so fundamentally terrifying that it posits the potential end of not just life or planets or stars, but of reality as we understand it. To grasp this, we need to rethink our notion of nothingness. We imagine the vacuum of space as pure, empty void. But according to modern physics, what we call a vacuum is not truly empty. It is a seething, bubbling foam of fundamental fields, and the properties of those fields determine everything in our universe: the strength of gravity, the mass of an electron, the very fact that atoms can bond to form molecules. These fields exist in what physicists call their lowest possible energy state, a stable valley from which they cannot fall. But what if our universe is not in the true valley but a false one? Imagine a vast, rolling hillside. Our universe isn't resting peacefully at the very bottom. Instead, it's trapped in a small, stable-looking depression partway down the hill. It feels stable. It has felt stable for over 13 billion years, but it's not the absolute lowest point. This metaphorical hillside is what physicists call the Higgs field, which gives particles their mass. Our entire reality is built upon the specific properties of this field in its current state. The terrifying possibility is that a truer, lower energy state exists a deeper valley far below our own. The horror of vacuum decay is the possibility that a random quantum event anywhere in the universe could provide the tiny push needed to knock our local field out of its false valley. This event would create a microscopic bubble of true vacuum. Inside this bubble, the fundamental constants of physics would be instantly and permanently rewritten. The laws that allow for atoms, molecules, stars, and life would cease to exist, replaced by a new, alien set of rules. This bubble would then expand in all directions at the speed of light, a wall of fundamental transformation that is utterly impossible to outrun or detect in advance. There would be no flash, no bang, no dramatic warning. One moment reality exists as we know it. The next, the sphere of new physics has arrived, and everything within it is instantly and irrevocably erased. The structure of every atom in your body, in the earth, in the sun, would dissolve, reconfigured into something entirely unrecognizable, likely a state incapable of supporting any complex structure whatsoever. It would be an end to existence, not with a cataclysm, but with a silent, physics-level rewrite. The most chilling aspect is the trigger. This universe-ending event wouldn't require a supernova or a collision of galaxies. It could be sparked by a completely random quantum fluctuation in deep space, an event with no cause happening purely by chance. Or, terrifyingly, it could be triggered by us. High-energy particle collisions, like those conducted in the Large Hadron Collider, have been the subject of public fear. though physicists widely agree the energies involved are far too low to pose any risk. The theoretical danger lies in the possibility that if we ever advance to a civilization capable of manipulating energies trillions of times greater, our own experiments could become the spark that annihilates the cosmos. The probability of vacuum decay happening spontaneously is considered extraordinarily low. If it were high, it likely would have happened already in some distant part of the universe. But low probability is not the same as zero. It represents a permanent, existential threat woven into the very fabric of our reality, a sword of Damocles hanging over the entire cosmos, held by a thread that could be cut by a random, unknowable event at any moment, rewriting the universe into a form where we and everything we've ever known could never have existed. From the abstract horror of a universe-ending phase transition, we now turn to a more tangible yet equally chilling specter, a celestial corpse that refuses to rest in peace. Imagine a star that has already lived its life, a burned-out cinder that has shed its outer layers and collapsed into a dense, Earth-sized ember known as a white dwarf. It is a stellar ghost, a remnant that should slowly cool and fade into the blackness over trillions of years. But in the cosmic darkness, this ghost can be reanimated. In a binary system where two stars are locked in a mutual gravitational dance, the white dwarf can begin to act as a vampire, using its gravity to slowly siphon hydrogen and helium from its living companion star. This stolen material doesn't simply pile up, it accumulates on the white dwarf's incredibly dense surface under immense pressure and heat. For a time, this process creates a beautiful but deceptive phenomenon, periodic novas, where the accumulated material ignites in a flash of nuclear fusion, causing the star to brighten tremendously before settling back down. It's a temporary flare-up, a cosmic cough, but this is not the true reanimation. The true terror begins if the rate of theft is just right, allowing the stolen mass to build up steadily over millions of years. The white dwarf, a corpse composed mostly of carbon and oxygen, is pushed closer and closer to a catastrophic threshold. With every ton of stolen matter, the internal pressure and temperature skyrocket. The star is essentially playing with fire on a planetary scale, edging toward a specific critical mass known as the Chandrasekhar limit. This is the point of no return, the moment the stellar vampire's feast becomes its self-immolation. The entire white dwarf, no longer able to support its own weight, undergoes a runaway thermonuclear reaction. In less than a second, the entire star is not just exploding, but is utterly obliterated in a cataclysm so uniform and so powerful that it outshines its entire host galaxy. This is a Type Ia supernova, the final, screaming resurrection of a dead star. What makes this process so chillingly important is its role as a standard candle. Because these supernovae always explode at almost exactly the same critical mass, they always release nearly the same amount of light. This consistency allows astronomers to use them as cosmic mile markers. By observing how bright they appear from Earth, we can calculate their true distance with incredible precision. It was precisely this tool that led to the Nobel Prize-winning discovery of dark energy in the late 1990s. Astronomers, expecting to measure the universe's deceleration, found instead that the most distant Type Ia supernova were fainter than they should have been, meaning the universe's expansion is not slowing down but accelerating. So, these zombie stars, these resurrected corpses, delivered one of the most profound and unsettling messages in modern cosmology, that the universe is being torn apart by a mysterious, repulsive force. The violence of their rebirth is thus a double-edged sword. On one hand, they are crucial recycling plants for the cosmos. The incredible energies of the explosion forge elements far heavier than iron, the gold in your jewelry, the uranium in nuclear reactors, the silicon in computer chips. These elements are blasted out across interstellar space, seeding future generations of stars and planets with the raw materials for rocky worlds and, potentially, life. Our own solar system formed from a cloud of gas and dust that was enriched by the death throes of such stellar ancestors. We are literally made from the ashes of these cosmic vampires. Yet, this vital recycling comes with a terrifying caveat. If one of these events were to occur too close to our solar system within a few dozen light years, the blast of radiation and high-energy particles would be catastrophic. The gamma rays and cosmic rays would scour our planet, severely damaging the ozone layer and bathing the surface in mutagenic radiation, likely triggering a mass extinction. The very elements that are essential for life, when forged in a furnace that is too near, become the instruments of death. The zombie star, therefore, stands as a stark and eerie monument to the duality of the cosmos. It is a mechanism of both creation and destruction, a dead thing that through a violent act of theft is reborn into a beacon that illuminates the fate of the universe, while simultaneously scattering the seeds of future worlds with one hand and the potential for annihilation with the other. But for all the colossal structures pulling us through the cosmos, there exists a counterpart of equal and opposite dread, a profound, echoing nothingness. Our next destination is a place that should not exist, a hole punched in the universe known as the Boötes Void. After mapping the locations of thousands of galaxies, astronomers in the 1980s discovered a staggering anomaly. In the direction of the constellation Boötes, they found a spherical region of space so empty, so devoid of galaxies, that it defies our standard models of the cosmos. This is not a small pocket of darkness. The Boötes Void is a staggering 330 million light-years across. To grasp that scale, if you were to place our Milky Way at the center of this void, the nearest wall of this cosmic cavern would be so far away that for most of human history, we wouldn't have even known other galaxies existed beyond our own. This immense sphere of near-nothingness is often called the Great Nothing, and the terror it inspires is not of a lurking monster but of abandonment. It is the existential fear of being utterly alone, magnified to a cosmic scale. Our universe, according to the leading theories, should be relatively uniform on the largest scales, a cosmic web of galaxy-filled filaments and clusters with bubbly voids in between. But the Boötes Void isn't a bubble, it's a chasm. It is far, far emptier than such models predict. While a typical void might be 100 million light-years wide, the Boötes Void is more than 3 times that size, and instead of containing dozens of galaxy clusters, surveys have found only about 60 galaxies in that entire unimaginable volume. That means the average distance between any 2 galaxies in the void is an unbearable 250 million light-years. If you were a civilization born on a planet inside the Boötes Void, your night sky would be almost perfectly black. With no nearby galaxies to adorn the darkness, your telescopes would see nothing but an unbroken emptiness in every direction. You might logically conclude that your galaxy was the only one in existence, a solitary island of light and life in an infinite, eternal dark. The true nature of the universe, a bustling metropolis of trillions of galaxies, would be completely hidden from you, your science and philosophy forever shaped by the crushing isolation of your location. This presents a profound cosmological puzzle. How does a void this large and empty even form? The leading theory points back to the very beginning of everything. In the infant universe, tiny quantum fluctuations were stretched to enormous sizes during a period of faster-than-light expansion called inflation. These ripples in density became the blueprints for all future structure. The dense spots eventually collapsed into galaxy clusters and superclusters, while the underdense regions expanded into voids. For the Boötes Void to exist, it must have originated from an exceptionally large and deep underdensity in that primordial fabric. Think of the universe's structure as the foam on a cappuccino. Most of the bubbles are relatively small and uniform. The Boötes Void is like a single, gigantic bubble that has swallowed dozens of the smaller ones, creating a cavernous, empty space that challenges our understanding of how that foam is supposed to form. Another, more speculative and unsettling idea is that the void isn't actually empty but filled with something we cannot see. What if the void is the territory of a truly dominant form of dark matter, a type that repels normal matter rather than attracting it? Or a region where dark energy, the force accelerating the universe's expansion, began its work early and with greater ferocity, pushing galaxies apart before they could ever form? These are fringe ideas, but they highlight how the void forces us to confront the limits of our knowledge. The sheer scale of this emptiness is so immense that it isn't just a curiosity, it is an active participant in the fate of the cosmos. The galaxies that do cling to existence within the void are profoundly affected by their environment. They are, in a very real sense, orphan galaxies, cut off from the continuous flow of intergalactic gas that normally fuels star formation. Deprived of this fresh material, these isolated galaxies have likely burned through their star-forming fuel, becoming old, red, and dead, their stellar populations aging in quiet solitude. They are the ghost towns of the cosmos, their light slowly dimming in the overwhelming dark. The Boötes void, therefore, is not a passive absence. It is an active, expanding region of cosmic impoverishment, a desert whose very nature strangles the potential for new life and light. It stands as a chilling counterpoint to the dense clusters and great attractors, a stark reminder that the universe is not just defined by what is there, but also by what is terrifyingly, inexplicably not. After confronting the chilling emptiness of the Boötes void, we must now turn our attention to the one entity that fills all voids, seen and unseen. It is the hidden master of the cosmos, the ghost in the machine of the universe, a substance that commands the very motion of galaxies yet leaves no trace of its presence. This is the profound and unsettling enigma of dark matter. We have mapped the stars, we have charted the galaxies, and we have measured the cosmic background radiation left over from the Big Bang. Yet, when we add up all the ordinary matter, every star, every planet, every speck of cosmic dust, we find it accounts for less than 5% of the total mass and energy in the universe. The rest is a mystery dominated by this invisible something that we cannot see, touch, or directly interact with, yet we know it is there because of its immense gravitational pull. The evidence for its existence is written in the very fabric of the cosmos. In the 1930s, astronomer Fritz Zwicky was studying the Coma Cluster, a vast collection of galaxies. He noticed that the individual galaxies were moving so fast that the cluster's own gravity should not have been strong enough to hold them together. According to all known physics, the cluster should have flown apart eons ago. Zwicky proposed the existence of Dunkel Materie, or dark matter, an unseen mass providing the extra gravitational glue. Decades later, Vera Rubin provided even more compelling evidence by studying the rotation of individual galaxies. She found that stars at the outer edges of spiral galaxies orbit just as fast as those near the center, a finding that defied the laws of motion. If only the visible matter were present, those outer stars should be flung off into deep space, much like a ball on a string would fly away if you spun it too fast. The only explanation is that each galaxy is embedded within a gigantic, invisible halo of matter, a sphere of dark stuff that extends far beyond the visible edge of stars, its gravity holding the entire structure together. This realization transforms our view of the cosmos. The glittering spiral arms of a galaxy are not the main event. They are merely the illuminated decoration on the surface of a far larger, darker, and more massive beast. We are not living in a universe of stars and galaxies. We are living inside a universe of dark matter, where the luminous matter we cherish is just the occasional speck of light in an endless, invisible ocean. The true terror of dark matter does not come from a direct threat like an asteroid or a gamma-ray burst. Its horror is far more subtle and philosophical. It forces us to accept that the vast majority of the universe, the very framework that dictates the fate of everything we see, is made of something we fundamentally do not understand. We are like characters in a play, performing on a stage we cannot see, directed by forces we cannot perceive. For all our technological advancement and scientific achievement, we are blind to 95% of the cosmic reality. We feel its gravitational hand guiding the motion of galaxies and the evolution of the entire cosmos, but we have no idea what that hand is made of. We have been searching for decades, running incredibly sensitive experiments deep underground to shield them from cosmic interference, hoping to catch a fleeting interaction as a dark matter particle, known as a WIMP or a weakly interacting massive particle, bumps into an atom of normal matter. So far, the detectors have remained silent. We have built powerful particle colliders like the Large Hadron Collider, hoping to create dark matter in the lab by replicating the conditions of the early universe. We have yet to see a confirmed signal. We have even looked for indirect evidence, such as the unique radiation that might be produced if two dark matter particles were to collide and annihilate each other in the dense centers of galaxies. The results are ambiguous at best. This persistent failure to identify what dark matter actually is has led to a creeping unease in the scientific community. What if it is something even stranger than we imagined? One of the more speculative and chilling possibilities is that dark matter isn't entirely inert. What if certain forms of it can interact with itself through a hidden force, a dark electromagnetism, creating the possibility of complex structures? In this scenario, there could be an entire dark sector operating in parallel with our own, a shadow universe with its own dark planets, dark stars, and even dark life forms, all coexisting with us, passing through our world without a trace because they simply do not interact with light or normal matter. We could be sharing this very room, this planet, with entire civilizations of dark matter beings, and we would never know. They would be ghosts in the truest sense, permanent residents of a reality that is forever locked away from our senses. While this idea belongs more to the realm of speculative physics, it underscores the core fear, our profound ignorance. Dark matter's dominance means it is the ultimate architect of our cosmic environment. It was the gravitational seeds of dark matter that first drew in the gas that formed the earliest stars and galaxies. It is the intricate web of dark matter filaments, stretching across billions of light years, that dictates where galaxies can form and how they cluster together. Our very existence, the fact that our Milky Way galaxy formed in a location rich enough with gas and dust to create our Sun and Earth, is a direct consequence of the initial, random distribution of this invisible substance. We owe our existence to a cosmic phantom, and this phantom may hold the key to our ultimate fate. The amount and distribution of dark matter are crucial factors in the great cosmic tug of war between the expansion of the universe, driven by dark energy, and the pull of gravity. It is the deciding factor in whether the universe will expand forever into a cold, dark nothingness or eventually reverse course in a big crunch. Dark matter wrote the first chapter of the universe in the moments after the Big Bang, and it will almost certainly write the final one. It is the silent, unseen king of the cosmos, and we are only just beginning to comprehend the edges of its vast, dark domain. But if dark matter is the hidden framework of the cosmos, and zombie stars are the agents of cosmic recycling, then where is everybody? This simple, profound question leads us to one of the most deeply unsettling concepts in all of science, the Fermi Paradox, named for physicist Enrico Fermi, who reportedly blurted out, "But where is everybody?" During a lunchtime conversation in 1950, this paradox captures the jarring contradiction between the high probability of alien life and the total lack of any evidence for it. The universe is ancient, nearly 14 billion years old, and unimaginably vast, with hundreds of billions of galaxies, each containing hundreds of billions of stars. Many of those stars are billions of years older than our Sun, and a huge number are orbited by planets in the habitable zone where liquid water, and therefore life, could exist. Given these staggering numbers and the immense head start other worlds would have had, the galaxy should be teeming with life. It should be a bustling interstellar metropolis filled with the radio chatter of countless civilizations, the wake of starships traveling between systems, and perhaps even the grand, galaxy-altering engineering projects of civilizations millions of years more advanced than our own. And yet, when we point our telescopes at the sky, we are met with nothing but an eerie, unbroken silence. This silence is not just empty, it is loud with implication. It suggests that something is terribly wrong. Over the decades, scientists and thinkers have proposed many solutions to this paradox, but the most terrifying category of answers is known as the Great Filter. This hypothesis suggests that there is some kind of barrier, a single, incredibly difficult step or a recurring trap, that prevents life from progressing to the stage of colonizing the galaxy. The filter is so powerful that it culls almost every potential civilization, and the cosmic silence is the result. The terrifying question for us is where this filter lies. Is it in our past, or is it waiting for us in our future? If the Great Filter is behind us, it means that the step from non-life to intelligent, technological life is astronomically rare. Perhaps the genesis of life itself from primordial chemistry was a one-in-a-trillion fluke. Or maybe the evolutionary jump to complex multicellular organisms, which took billions of years to occur on Earth, is the true bottleneck. If this is the case, then humanity is a cosmic miracle, a lone, flickering candle in an immense and otherwise lifeless darkness. This is a comforting thought in one sense, as it means our future is open. But it is also a profoundly lonely one, placing the entire weight of consciousness in the universe on our fragile shoulders. The far more frightening possibility is that the Great Filter lies ahead of us. In this scenario, the development of intelligent life might be relatively common, but the development of a stable, long-lived technological civilization is not. There may be a predictable point in a civilization's evolution where it gains the power to destroy itself and inevitably does so. This is the self-destruction hypothesis. We can already see the potential paths. It could be a nuclear holocaust, a war fought with weapons that can obliterate a planet's biosphere. It could be a runaway climate catastrophe, engineered or accidental, that renders a world permanently uninhabitable. Or it could be something we haven't even conceived of yet, a disaster born from nanotechnology, where self-replicating machines reduce the entire planet to a gray goo, or the emergence of a superintelligent artificial intelligence whose goals do not align with our survival. The silence of the cosmos, in this view, is not a sign of our uniqueness but a graveyard. Every civilization that reaches our level of technological prowess eventually discovers a technology that becomes its own tombstone. The stars are silent because no one survives to speak. This idea transforms the Fermi Paradox from a curiosity into a dire warning. We are not listening for neighbors, we are studying our own potential future by observing the universal absence of others who have walked this path before us. Other explanations, while less apocalyptic, are equally chilling in their own right. There is the possibility of a predatory civilization, the concept of the dark forest. This theory imagines the galaxy as a dark forest where every civilization is a hidden hunter. Any civilization that reveals its location by broadcasting signals into space, for example, risks being targeted and annihilated by a far more advanced power that sees any potential competitor as a threat that must be eliminated preemptively. In such a universe, the smartest strategy is absolute silence. Everyone is hiding, listening intently, but no one is speaking for fear of attracting the attention of something far more terrifying. Another deeply unsettling idea is that we are simply uninteresting, or worse, that we have been intentionally isolated. This is the zoo hypothesis, which suggests that advanced galactic civilizations are aware of us but have placed our solar system in a kind of cosmic quarantine. a preserve to be observed but not contacted, perhaps until we reach a certain level of maturity or until we destroy ourselves. We are the exhibit and they are the silent curators. These solutions paint a picture of a cosmos that is not just physically hostile, but socially hostile. A place where the rules of engagement are so brutal or so aloof that communication and community are impossible. The weight of this cosmic silence presses down on every search we conduct. Projects like SETI, the search for extraterrestrial intelligence, scan the heavens for any artificial signal, any whisper of a technological signature. But after decades of listening, the result is the same profound quiet. This ongoing null result is in itself data. It tells us that whatever is out there, it does not look or sound like our optimistic visions of a communicative, star-faring society. The Great Filter hypothesis forces us to look inward, to confront our own growing pains as a technological species. The period we are living in right now, where we possess the power to annihilate ourselves but have not yet developed the wisdom or the technology to reliably escape our planet, may be the most dangerous in all of human history. It is the bottleneck through which we must pass. The Fermi Paradox holds up a mirror to humanity, and the reflection we see is one of a species standing at a precipice, peering into a silent darkness, and wondering if that silence is the answer to the most important question we will ever ask. Leaving behind the silent, existential dread of the Fermi Paradox, we now witness a cosmic event of spectacular and violent ejection. Our next entry is not a lurking monster or a silent void, but a brilliant, solitary fugitive, the hypervelocity star. These are not your average, gentle suns tracing orderly orbits around the galactic center. They are cosmic cannonballs, stars catapulted from their home galaxies at speeds so immense they can defy the gravitational pull of the entire Milky Way, screaming into the intergalactic darkness on a one-way trip to nowhere. To achieve such a feat requires a force of almost unimaginable power, and astronomers have identified the prime suspect, the supermassive black hole that lurks at the heart of our galaxy, known as Sagittarius A star. The most widely accepted mechanism for creating these stellar outlaws is a gravitational slingshot effect within a triple star system. Imagine a trio of stars bound together by gravity, swinging too close to the galactic center's monstrous black hole. In this chaotic dance, the black hole's immense gravity can capture one of the stars, pulling it into a tight orbit while simultaneously flinging its two companions outward at phenomenal speeds. In a perfectly balanced interaction, one of those ejected stars can be accelerated to over 1,000 kilometers per second, a velocity so great that it breaks free from the Milky Way's gravitational embrace forever. It becomes a runaway star, a solitary beacon of light and heat on an eternal journey through the cold, empty vastness between galaxies. The first of these intergalactic fugitives was discovered in 2005, a massive star racing through the outskirts of our galaxy at over 2.5 million miles per hour. This discovery confirmed a theoretical prediction and revealed a new class of celestial object, one born from the most powerful engines in the universe. The terror these stars evoke is not one of direct collision. The space between stars is far too vast for that to be a real concern. Instead, it is the profound sense of loneliness and the sheer, indifferent violence they represent. A hypervelocity star is a sun condemned, banished from the stellar metropolis of its birth galaxy, and sent careening into a forever night so empty and dark that the very concept of a neighboring star becomes a forgotten memory. For any planets that might have been orbiting such a star at the moment of its ejection, the fate is a special kind of hell. They would be torn from their galactic community in an instant. The night sky, once filled with the soft glow of the Milky Way, would, over millennia, fade to an absolute, unbroken black. No other stars, no neighboring suns, just the perpetual, cold light of their own parent star. The concept of a year would become meaningless as there would be no other celestial reference points to mark the passage of time. Any life on such a world would be inhabitants of the ultimate island, isolated not by an ocean, but by millions of light years of nothingness, their entire universe contained within the single, shrinking point of light from their own receding galaxy. This process highlights a terrifying capability of supermassive black holes. They are not just passive anchors for galaxies, they are active engines of stellar destruction and redistribution. They can, with the casual flick of a gravitational wrist, dismantle entire solar systems and fling their constituent stars into the abyss. This underscores a recurring theme of cosmic horror. The forces that shape our universe operate on a scale of power and indifference that is almost impossible to comprehend. A hypervelocity star is a permanent exile, a blazing tombstone marking the site of a gravitational encounter with a monster, carrying the story of its violent birth across the intergalactic sea. While the silent flight of hypervelocity stars speaks of a lonely fate, our next cosmic terror threatens a far more universal and intimate form of destruction, one that turns the very force of expansion into an instrument of ultimate dissolution. This is the nightmare scenario known as the Big Rip. We have learned that our universe is not static, it is stretching, with galaxies flying away from one another at an ever-increasing rate, driven by the mysterious repulsive force we call dark energy. For now, this expansion is a grand cosmological phenomenon, noticeable only on the vastest scales between galaxy clusters. But the Big Rip hypothesis asks a terrifying question. What if this acceleration doesn't just continue but intensifies? What if the dark energy driving this expansion isn't constant, but grows stronger over time, becoming the dominant force not just between galaxies, but within them, within our solar system, and ultimately within the very atoms that make up our bodies? This is not an end by fire or ice, but by the unraveling of reality itself, a silent, inexorable tearing apart of every structure that gravity and the fundamental forces have so carefully built over billions of years. The true horror of the Big Rip lies in its timeline, a countdown to annihilation that would unfold with chilling, predictable precision. It would begin on the grandest of scales, billions of years from now. The first casualties would be the largest gravitationally bound structures in the universe. The cosmic web, that beautiful filamentary structure of galaxies, would be the first to come undone. The immense threads of dark matter and galaxies that stretch across the cosmos would be stretched and severed as the expansion of space between them overcame the gravitational glue holding them together. Soon after, our own local group of galaxies, which includes the Milky Way and Andromeda destined for a future merger, would be torn asunder. The delicate gravitational dance that has bound these galaxies together for eons would be shattered, and each galaxy would be flung into an ever-widening, ever-emptier cosmos, their paths diverging at speeds that would make any future reunion impossible. But the rupture would not stop at the galactic frontier. As the expansion force grows even stronger, it would begin to attack gravity on its home turf. About 60 million years before the final moment, the accelerating universe would rip our Milky Way apart. The gravitational bonds holding the stars together would be overwhelmed, and every star in the galaxy would be flung into the void, each becoming a solitary, receding point of light in an exponentially darkening sky. Our solar system would be next. In the final months, the Sun's gravity would lose its grip on the planets. Earth would be ripped from its orbit, set adrift on a trajectory leading nowhere. In the last minutes, the destructive force would turn inward. The Earth itself would be torn apart, its gravity no longer strong enough to hold the planet together against the expansion of space itself. The ground would heave and fracture on a global scale, and the entire planet would be blasted into fragments. The cataclysm would then become personal. In the final, unimaginable seconds, the expansion force would exceed the strength of the chemical bonds holding your body together. You would not be crushed or vaporized, you would be pulled apart, disassembled at a molecular level. And in the last fleeting fraction of a second, atoms themselves would be dismantled. the electromagnetic force that binds electrons to nuclei, and the strong nuclear force that holds protons and neutrons together in the atom's core would both be overcome. Every atomic nucleus, every fundamental particle, would be pushed apart by the expanding space between them, leaving a cold, infinitely dispersed, and utterly featureless void. The universe would not end with a collapse, but with a silent, perfect smoothing into nothingness, a state of zero structure and zero potential for anything ever to exist again. This apocalyptic vision hinges entirely on the nature of the dark energy that is currently accelerating the universe's expansion. The simplest model, proposed by Einstein himself, is the cosmological constant, a form of dark energy whose density remains stable over time. In this model, the universe continues to accelerate, but the force never becomes strong enough to overcome the bonds within galaxies, let alone atoms. Galaxies would drift apart into isolation, but they would remain intact, leading to a cold, lonely, but not shredded future known as the heat death. The Big Rip, however, requires a more potent and terrifying form of dark energy known as phantom energy. This is a hypothetical substance whose energy density doesn't just remain constant, but actually increases as the universe expands. Think of it not as a steady push, but as a pressure that builds and builds without limit. It is this runaway nature of phantom energy that gives it the power to eventually overwhelm every other force in the universe, from the gentle tug of gravity to the fierce grip of the strong nuclear force. While phantom energy remains a speculative idea, its mere possibility forces us to confront a fundamental instability that could be woven into the fabric of reality. The engine of cosmic creation, the expansion that began with the Big Bang, could potentially contain the seeds of its own ultimate, self-destructive climax. We are left with the unsettling realization that the fate of every atom, every star, and every galaxy may rest on the precise and still unknown properties of the universe's most mysterious component. From the silent, accelerating doom of the Big Rip, we turn to a terror that is the exact opposite, a celestial metronome of unimaginable violence, a beacon that marks not a safe harbor, but a zone of absolute annihilation. These are pulsars, the spinning corpses of massive stars that refuse to fade away quietly. When a giant star explodes in a supernova, its core can be crushed into a sphere of pure neutrons just a dozen miles across, yet containing more mass than our entire sun. This neutron star is so dense that a single teaspoon of its material would weigh billions of tons on Earth. But the true horror begins when this stellar corpse is set spinning, and this is where the pulsar earns its name. As the star collapses, it conserves its angular momentum, causing it to rotate at a dizzying speed, often hundreds of times per second. Its already intense magnetic field is compressed into an unimaginably powerful funnel, trillions of times stronger than Earth. Charged particles caught in this field are accelerated to near light speed, erupting from the magnetic poles in two powerful, focused beams of radiation that span the entire electromagnetic spectrum, from radio waves to deadly gamma rays. If the spin axis is misaligned with the magnetic axis like a dizzyingly fast lighthouse with a tilted beam, these jets sweep across the cosmos. From a distance, we detect this as a perfectly timed pulse, a blink of radiation with a precision that rivals atomic clocks. This is the pulsar, a cosmic zombie, a dead star reanimated into a spinning engine of destruction, broadcasting its presence with a rhythmic scream into the void. For any world unfortunate enough to orbit one, this mesmerizing pulse is a death knell. The primary threat from a pulsar is not merely the focused beams, but the entire hostile environment it creates, a phenomenon known as the pulsar wind. This is a relentless gale of high-energy particles and radiation that flows outward from the neutron star continuously, a toxic hurricane that fills its entire surrounding space. Imagine a star that doesn't just shine with light, but perpetually emits the equivalent of a particle accelerator's output across light years. any planet orbiting within the reach of this wind would be scoured clean. Its atmosphere would be stripped away atom by atom, blasted into space by the constant pressure. The surface would be baked under an unending shower of X-rays and gamma rays, sterilizing the rock to a depth of many feet, ensuring that no life, not even the hardiest extremophile, could ever gain a foothold. The very concept of a habitable zone vanishes near a pulsar. The entire system is a sterile, radioactive desert. This is not a theoretical danger. We have observed real-world examples of planets in these terrifying environments. One of the first exoplanets ever discovered, back in 1992, was found orbiting a pulsar named PSRB 1257+12. This planet and its two siblings exist in a perpetual state of siege. They are bathed in the pulsar's relentless wind, enduring conditions so extreme that they are likely barren, irradiated chunks of rock, their surfaces possibly composed of crystallized carbon like diamonds forged in the intense pressure and heat. Their very existence is a puzzle. How could any world form or survive the supernova explosion that created the pulsar in the first place? They are perhaps the ultimate survivors, worlds that somehow weathered a stellar apocalypse only to find themselves in a new perpetual hell. But the focused beams add another layer of specific periodic terror. If a planet's orbit were to carry it repeatedly through the path of one of those sweeping lighthouse beams, the effect would be a nightmare of cyclical destruction. For most of its orbit, the world would be subjected to the constant, deadly background of the pulsar wind. But then, as it swings into the path of the beam, it would be hit by a flash of radiation millions of times more intense. This would be a regular, predictable apocalypse, a strobe light of pure energy that would periodically superheat the atmosphere and surface, triggering global firestorms and creating unimaginable weather patterns. Life could never adapt to such a rhythm. The energy delivered in each pulse would be enough to shatter complex molecules and reset the evolutionary clock over and over again. The pulsar's greatest trick, its mesmerizing clockwork precision, becomes the source of its most insidious horror. This incredible regularity is what makes them so useful to astronomers for testing theories of gravity and for cosmic navigation. But for a potential inhabitant of such a system, that precise ticking is the countdown to the next sterilization event. The pulsar is a reminder that in the cosmos, beauty and order are not guarantees of safety. They can be the hallmarks of a perfectly tuned and perfectly efficient killing machine. Now we turn from the distant horrors of deep space to a threat that is building right in our own celestial backyard, a danger of our own making that could literally lock us on our planet. This is the Kessler syndrome, a theoretical nightmare scenario that turns the space around Earth into an impassable shooting gallery. The concept is named after NASA scientist Donald Kessler, who first outlined the terrifying domino effect in 1978. The problem begins with the fact that we have been incredibly messy neighbors in low Earth orbit. For decades, we have been launching satellites, rockets, and space stations, leaving behind a swirling cloud of discarded rocket boosters, dead satellites, fragments from explosions, and even flecks of paint and frozen coolant. Each piece of this debris, no matter how small, is a potential bullet. In the vacuum of space, there is no air resistance to slow these objects down. They travel at mind-boggling speeds, roughly 17,500 miles per hour, which is about 10 times faster than a high-powered rifle bullet. At that velocity, a metal bolt just a few centimeters across carries the kinetic energy of a grand piano dropped from a 10-story building. A collision with an object that size would be catastrophic for any spacecraft, the International Space Station, or an astronaut on a spacewalk. It wouldn't just make a hole, it would be a hyper-explosive event, shattering the target into hundreds or thousands of new fragments. And this is where the true horror of the Kessler syndrome takes hold. It's a chain reaction. One collision creates a cloud of new debris, each piece now a new projectile capable of causing another collision, which in turn creates even more debris. Over time, this cascade could reach a critical tipping point where the density of debris in orbit becomes so high that collisions become self-sustaining and inevitable, even if we never launched another rocket. The space around our planet would transform from a highway to the stars into a swirling, impenetrable shield of shrapnel, a permanent and ever-growing minefield that would render spaceflight in those orbits impossible for generations, perhaps even for centuries. The immediate consequence of such a scenario would be the loss of our orbital infrastructure, a loss that would send our modern world back into a technological dark age. We have become utterly dependent on the silent fleet of satellites circling overhead. They are not just for television broadcasts or finding the nearest coffee shop. The Global Positioning System, or GPS, is the foundation for global finance, banking, stock markets, and high-frequency trading, all of which rely on the nanosecond timing signals from these satellites. The entire global shipping and transportation network, from container ships to airliners to your own car's navigation, depends on GPS. Take that away, and the logistical framework of our civilization begins to crumble within hours. Our weather forecasting and climate monitoring would be blinded overnight. Satellites provide the vital data that allows us to track hurricanes, predict storm paths, and monitor long-term climate change. Without them, we would be flying blind into increasingly volatile weather, with no early warning for disasters that threaten millions of lives. International communication would be severely hampered, disrupting everything from internet backbones to diplomatic channels. But the most profound loss would be our access to space itself. The International Space Station, a symbol of international cooperation and a platform for vital scientific research, would be immediately vulnerable, its crew trapped with no safe way to return to Earth or receive supplies. Future missions to the Moon or Mars would be cancelled indefinitely. We would be trapped, our species grounded, staring up at the stars through a cage of our own creation. Our dreams of becoming a spacefaring civilization shattered by a cloud of our own discarded trash. This is not a distant science fiction future. The first major warning shot was fired in 2009 when a defunct Russian communications satellite, Cosmos 2251, collided with an operational American commercial satellite, Iridium 33, over Siberia. The collision, occurring at a combined speed of over 26,000 miles per hour, completely obliterated both spacecraft and created thousands of new, trackable pieces of debris, along with countless smaller fragments. This single event increased the known debris population in low Earth orbit by a massive amount overnight, creating a cloud of shrapnel that will remain a hazard for decades. An even more destructive event had occurred 2 years prior, in 2007, when China conducted an anti-satellite missile test, deliberately destroying one of its own aging weather satellites. That irresponsible act created the single largest debris cloud in history, with over 3,000 trackable objects and an estimated 150,000 smaller pieces scattered across a heavily used orbital band. These two events served as a stark and terrifying proof of concept for Kessler's theory, demonstrating that collisions do happen and that they can massively and permanently pollute the orbital environment. Today, spacefaring nations and private companies are forced to regularly maneuver the International Space Station and other valuable satellites to avoid known debris. These are not rare events, they are routine, necessary maneuvers to dodge the ever-growing swarm of junk. The situation is a slow-motion emergency, a ticking time bomb where every near miss is a reminder of how close we are to the precipice. So, what can be done to avert this catastrophic future? The solutions are as challenging as the problem itself. The first and most critical step is prevention. There is a growing international push for new rules and norms, often called space traffic management. This includes designing new satellites to be deorbited at the end of their lives, either by guiding them to burn up in the atmosphere over a remote ocean area, or by moving them to a designated graveyard orbit far away from active spacecraft. There are also proposals for active debris removal, which sounds like science fiction but is desperately needed. These concepts include using lasers to nudge smaller pieces into the atmosphere, launching specialized spacecraft with nets, harpoons, or robotic arms to capture and to orbit large derelict objects like old rocket bodies, or even using powerful magnetic systems to interact with and slow down metallic debris. However, these technologies are in their infancy, incredibly expensive, and raise difficult legal and political questions. Who is responsible for cleaning up the debris, who pays for it, and who has the right to remove a defunct satellite that belongs to another country? The Kessler syndrome is therefore more than just an engineering problem. It is the ultimate tragedy of the commons played out on a global orbital scale. Every nation and every company benefits from using the space environment, but without a coordinated global effort to clean it up, the actions of a single irresponsible actor could spoil it for everyone. The silence that would follow a full-blown Kessler cascade would be profound. The heavens would still be there, but the constant, invisible chatter of our satellites would cease. The steady stream of data, the hum of communication, the guiding signals for our ships and planes, it would all be gone, replaced by the quiet whizzing of countless fragments, a permanent monument to our short-sightedness. While the silent cascade of orbital debris represents a danger of our own making, the cosmos itself engages in a far grander and more violent form of consumption. We now arrive at a process of cosmic predation on a scale so vast it redefines our understanding of galactic life and death, galactic cannibalism. This is not a metaphor. Our universe operates under a brutal gravitational hierarchy where larger, more massive galaxies actively consume and digest smaller ones, tearing them apart over billions of years in a slow-motion feast. The serene images of spiral galaxies we so often see are deceptive. They are not peaceful island universes, but the victors and survivors of a relentless cosmic struggle, their majestic structures often built from the devoured remains of their galactic neighbors. The evidence for this violent history is written in the halos of large galaxies like our own. Astronomers have found streams of stars like cosmic gossamer threads wrapping around the Milky Way. These are not random clusters, they are the gravitational entrails, the final glowing remnants of dwarf galaxies that ventured too close and were shredded by our galaxy's immense gravity. Their stars now assimilated into a vast spherical halo that extends far beyond the familiar spiral disk. Our galaxy is in fact a cannibal, having consumed dozens of smaller galaxies over its lifetime, and it continues to do so today. But this process is not a one-way street to destruction. It is a violent, creative, and ultimately transformative force that reshapes the very galaxies involved, a cycle of death and rebirth that governs galactic evolution across the universe. The ultimate expression of this cosmic destiny awaits us in the distant future, a collision course set billions of years ago. Our Milky Way and our nearest large galactic neighbor, the Andromeda Galaxy, are hurtling toward each other at a speed of about 250,000 miles per hour. In approximately 4.5 billion years, the two spiral giants will begin a gravitational tango that will last for billions more. A slow, majestic, and utterly terrifying dance that will completely alter the night sky for any life that remains on Earth. The initial approach will be a spectacle of unimaginable beauty and growing dread. Andromeda, which today appears as a faint, fuzzy smudge in the constellation of the same name, will grow progressively larger in the sky, eventually spanning the entire heavens as it draws nearer. The first actual collision will not be a head-on crash of stars, for the distances between individual stars are so immense that direct stellar impacts are extraordinarily rare. Instead, the galaxies will pass through each other, their stars weaving past one another like two vast swarms of bees interpenetrating without colliding. Yet, this initial passage will be far from peaceful. The real violence will be wrought by gravity, the invisible puppeteer that will tear both galaxies apart. The elegant spiral structures that have defined them for eons will be utterly destroyed. Their delicate disks of gas, dust, and stars will be pulled and twisted into long, streaming tails, a process evocatively known as tidal shredding. The galaxies will become distorted, grotesque versions of their former selves, their identities lost in a mess of gravitational turmoil. During this chaotic merger, the immense clouds of gas and dust within both galaxies will be violently compressed. This triggers ferocious waves of new star formation known as starbursts. Across the merging galaxies, millions of new stars will ignite in a brilliant, fiery blaze, outshining all the old stars combined. These are not the gentle, long-lived stars like our Sun, but massive, blue, and short-lived giants that burn furiously and die young in spectacular supernova explosions. This period of intense stellar birth is both creative and destructive. It forges new generations of stars and planets, enriching the galactic gas with heavy elements. Yet, for any existing planetary systems, it is a time of extreme peril. A planet orbiting a star in a stable, quiet region like our own could suddenly find itself near a newly ignited stellar inferno, its climate and atmosphere scorched by the intense radiation. More terrifyingly, the gravitational chaos can fling stars and their planetary systems out of the merging galaxy entirely, casting them into the cold, intergalactic void as rogue systems, forever lost to the galactic community. Alternatively, other star systems could be slingshotted inward toward the newly forming galactic core, into a densely packed and radiation-filled environment where planetary orbits are destabilized, leading to cosmic pile-ups and collisions. The fate of our own solar system in this melee is uncertain. Current models suggest we could be flung much farther from the galactic center, or even ejected entirely, becoming a lonely island in the dark. There is also a small chance we could be dragged inward toward the tumultuous core. In any scenario, the stable, clockwork environment that allowed life to flourish on Earth will be irrevocably shattered. The final act of this cosmic drama sees the two galaxies, now thoroughly merged and mixed, settle into a new, singular form. After several billion years of chaotic interaction, they will coalesce into a giant, football-shaped galaxy known as an elliptical galaxy. All the beautiful spiral structure will be gone, erased by the violence of the merger. This new galaxy, sometimes called Milkomda, will be a smooth, red and gold-hued collection of older stars, its era of frantic star formation long past, having exhausted its gas reserves in the final, brilliant starburst. The two supermassive black holes from the hearts of the original galaxies, having spiraled toward the center through dynamical friction, will eventually merge themselves, releasing a final, titanic burst of gravitational waves that will ripple across the cosmos. This transformation from spiral to elliptical is the ultimate fate of most large galaxies, a testament to the fact that the universe is not in a state of peaceful equilibrium, but in a constant, dynamic, and often violent state of flux. Galactic cannibalism is the primary engine of this change. It is a process that demonstrates a profound and humbling truth. Even the grandest structures in the universe are temporary. The Milky Way as we know it, the familiar band of stars that has inspired humanity for millennia, is destined to die, not in a fade to black, but in a fiery embrace with a neighbor, giving birth to something entirely new and alien. It is a fate written in gravity, a reminder that on the grandest scales, the cosmos is a place of both magnificent creation and terrifying, impersonal destruction. Amidst the grand, impersonal violence of galactic collisions and the silent creep of vacuum decay, there exists a different kind of terror, one born not of cosmic force, but of profound and fleeting connection. It is the terror of a single, cryptic message, a whisper that seemed to say hello before vanishing forever into the static. This is the story of the WOW signal, a 72-second burst of radio waves that remains, to this day, the most compelling and unsettling candidate for a transmission from an extraterrestrial intelligence. The event unfolded on a quiet August evening in 1977 at the Big Ear Radio Telescope in Delaware, Ohio. This was part of the ongoing search for extraterrestrial intelligence, or SETI, a patient, almost meditative effort to scan the skies for any pattern that could not be explained by nature. The system was automated, with the telescope slowly sweeping the sky and a computer printing out strings of numbers and letters representing signal strength. For days, weeks, there was nothing but the background hiss of the universe, but then on August 15th at 10:16 p.m., the silence was broken. As the telescope's gaze passed near the constellation Sagittarius, the recorder needle jumped. The signal was so powerful, so perfectly tuned, that it maxed out the equipment scale. It was a narrowband radio signal at exactly 1,420 MHz, a frequency that is scientifically significant because it is one of the main emission lines of neutral hydrogen, the most common element in the universe. It's a quiet channel, a natural spot where an advanced civilization might choose to broadcast a beacon, knowing that anyone else listening to the cosmos would understand its universal importance. For 72 seconds, the exact length of time the Big Ear telescope could focus on a single point in the sky, this signal blared, and then, just as abruptly as it arrived, it was gone. The event might have been lost in the reams of data if not for a volunteer named Jerry Amon, who was reviewing the computer printouts a few days later. As his eyes scanned the columns of alphanumeric code, he saw a sequence so startling that he circled it in red pen and in the margin wrote a single iconic word: "Wow." The sequence 6-5 was a specialized code indicating an intense, focused signal that rose and fell in a perfect curve as the telescope moved across it, a signature that screamed artificial. It was everything SETI researchers had been hoping to find: strong, narrowband, and unambiguously not from Earth. What followed this electrifying discovery was a decades-long descent into a profound and chilling mystery. The first order of business was to rule out a terrestrial source or a reflection from a passing satellite or aircraft. Every possible explanation was meticulously investigated and systematically eliminated. It wasn't a secret military transmission. It wasn't a signal bounced off a piece of space debris. It wasn't a natural astrophysical phenomenon like a pulsar or a quasar, which produce broad-spectrum radio noise, not a pure, clean tone on a single frequency. The signal's characteristics pointed unequivocally to an origin far beyond our solar system. The immediate and obvious next step was to listen again. The Big Ear telescope and later other, more powerful radio observatories around the world pointed their dishes back toward that same precise spot in the sky near the star cluster Chi Sagittarii. They listened for hours, then days, then years. They scanned the region across a wider band of frequencies. They employed more sensitive equipment, but they heard nothing. Not a whisper, not an echo. The WOW signal was a one-time event, a cosmic flash in the pan that has never, ever repeated. This absolute silence is the source of its deep and growing dread. If it was a deliberate beacon, why was it only switched on for 72 seconds? If it was an accidental leakage from an alien civilization, akin to our own television and radar broadcasts, what catastrophic event suddenly silenced their transmitter? The possibilities that emerge from this void of information are deeply unsettling. Perhaps it was a targeted message aimed not at us but at another destination, and we simply drifted through its beam for a fleeting moment. This would make us cosmic eavesdroppers, accidentally intercepting a communique not meant for our ears, a message whose context and meaning are forever lost to us. Or more grimly, perhaps the signal was indeed a beacon, and our failure to reply or our delay in doing so was interpreted as a sign of unworthiness or disinterest, leading the senders to move on. The most disturbing thought of all is that the signal was the last broadcast of a civilization that extinguished itself immediately after sending it. A final, desperate "we were here" cast into the void just as the lights went out forever. In this interpretation, the wow signal is not a hello, but a suicide note from an entire world. The legacy of the wow signal is therefore a paradoxical one. It is both the greatest success and the most frustrating failure in the history of SETI. It provided a tantalizing, data-driven hint that we might not be alone, a piece of evidence that has withstood over 4 decades of scientific scrutiny. Yet its singular, unrepeatable nature has prevented us from learning anything more. It offers no content, no message to decode, no direction to follow. It is a data point of one, an anomaly that refuses to be explained away or confirmed. This has turned it into a modern-day celestial ghost story, a scientific mystery that blurs into mythology. The signal forces us to confront the sheer, mind-crushing difficulty of interstellar communication. The vastness of space means that even a powerful, directed signal would be incredibly faint by the time it reached another star, and the alignment required for one telescope to be pointing at the exact right place at the exact right time to catch it is astronomically low. The wow signal may have been a 1 in a billion chance, a tiny window through which we glimpsed something monumental, and then the window slammed shut. Its enduring power lies in that brief, unresolved connection. For 72 seconds, something or someone, intelligent and technologically advanced, announced its presence from a point hundreds or even thousands of light years away. We heard it, we recorded it, and then we were left with only the silence, a silence that is now filled with the weight of that single, unanswered question. It stands as a permanent monument to the hope and the horror of the Fermi Paradox, a concrete example that the cosmos might not be empty, but that its inhabitants may be too distant, too transient, or too alien for us to ever truly know. It is the ultimate cosmic what-if, a ghost that has haunted astronomy for nearly half a century, a chilling reminder that the universe might be speaking, but we have only heard a single, solitary word. But for all the grand, cosmic threats we face from the void, the most certain and personally devastating one has been with us since the dawn of our world, a fate written not in the dark between galaxies, but in the very heart of our own star. We now arrive at the ultimate, inescapable end for our solar system, the day our sun dies. This is not a distant, abstract concept. It is the preordained future of our world, a transformation that will utterly erase the Earth as we know it. For billions of years, our sun has been a model of stability, a steady nuclear furnace fusing hydrogen into helium in its core, its outward pressure perfectly balanced against the immense crush of its own gravity. This delicate dance has provided the light and warmth that allowed life to flourish on our planet. But this stability is temporary. Like a log in a fireplace, the sun is slowly and inexorably consuming its fuel. In about 5 billion years, the hydrogen in its core will finally be exhausted. With no more fusion to push back, gravity will gain the upper hand, and the core will begin to contract, becoming hotter and denser. This collapse, however, triggers a catastrophic new chapter. The intense heat from the shrinking core will ignite a shell of hydrogen fusion around it, like setting fire to the sawdust around a dying log. This new, furious source of energy will have a dramatic and terrifying effect on the star's outer layers. The sun will begin to bloat, swelling to 100 times its current size. It will transform into a red giant, a monstrous, glowering orb that will dominate the sky. The timeline of this transformation is a slow-motion apocalypse. The initial swelling will be gradual, but its effects will be cumulative and irreversible. As the sun expands, its luminosity will increase dramatically. In its first stages as a subgiant, it will grow 50% brighter. Over the next several 100 million years, that brightness will continue to climb. Long before the sun physically touches our world, its intensified radiation will begin to bake it. The increased energy will trigger a runaway greenhouse effect, far more severe than anything we can cause today. The oceans will begin to boil. The water vapor, a potent greenhouse gas itself, will trap even more heat, accelerating the process. The skies will clear of clouds as the last of the liquid water vanishes, and the planet will be scoured by a relentless, desiccating wind. The familiar blue marble will turn into a cracked, barren wasteland, its surface temperatures soaring to hundreds of degrees, hot enough to melt lead. The atmosphere itself will be stripped away, blasted into space by the relentless solar wind from the now massively enlarged star. Earth will become a second Venus, and then something far worse, a airless, glowing ball of magma, its surface continuously remelted by the inferno from above. But the final, absolute end is still to come. The red giant sun will not stop at merely scorching the Earth, it will physically consume it. Current models show the sun's outer atmosphere swelling to a radius of nearly 1 astronomical unit, the exact distance from the sun to the Earth. Our planet will find itself orbiting inside the tenuous but incredibly hot outer layers of the star. The effect will be like trying to fly through an oven. The friction and dynamic pressure from plowing through this stellar material will drag on the Earth's orbit, causing it to spiral inward. There will be no dramatic collision, but a slow, agonizing dissolution. The rock and metal of our planet will be ablated away, layer by layer, melting and vaporizing, until the entire world is reduced to a stream of superheated plasma, its atoms mingling with the star that gave it birth. Mercury and Venus will have already shared this fate, consumed even earlier in the sun's expansion. The solar system we know, the clockwork of planets that has persisted for over 4 billion years, will be permanently, irrevocably unmade from the inside out. This stellar death rattle is not just an end, it is also a strange and beautiful beginning. In its final phases, the sun will become unstable, pulsating and throwing off its outer layers in a series of violent hiccups. These ejected shells of gas, illuminated by the still hot core, will form a magnificent planetary nebula, a brief, glowing shroud of incandescent gas that will light up the local cosmos for perhaps 10,000 years. It is the sun's final masterpiece, a cosmic work of art created from its own death throes. At the center of this glowing cloud, all that will remain is the star's collapsed core, a white-hot Earth-sized cinder known as a white dwarf. This stellar ember, composed mostly of carbon and oxygen, will have no internal fusion, shining only from its residual heat. It will be an incredibly dense object where a single teaspoon of material would weigh tons on Earth. And there it will sit for trillions of years, slowly cooling and fading from white to yellow to red, and finally to a cold black lump of crystallized carbon, a diamond in the dark. This final state is the ultimate fate of nearly all stars, a quiet, cold oblivion. The stark reminder here is not just of Earth's mortality, but of the entire solar system's. The planets, the asteroids, the comets, they are all temporary structures in a constant cosmic cycle of creation and destruction. Our world, with all its history, its life, its triumphs and tragedies, is a temporary phenomenon, a fleeting spark in the long, dark life of a star. The expansion of the sun is the definitive clock on our celestial neighborhood, a guarantee that the stage upon which humanity has played out its existence will one day be dismantled. It is a humbling and sobering thought, a cosmic memento mori that reminds us that all things, even the very stars we orbit, have a beginning, a middle, and a definitive, spectacular end. Just when we think we understand the grand motions of the cosmos, from the great attractor pulling our local supercluster to the relentless expansion driven by dark energy, the universe reveals another, even deeper layer of mystery. We now arrive at a phenomenon that seems to defy the very principle of cosmic uniformity, a ghostly current that hints at influences from outside everything we can see. This is the unsettling enigma of the dark flow. Imagine mapping the drift of countless galaxy clusters, the very largest structures in the universe, and discovering that they are not moving randomly. Instead, you find a vast, coordinated stream, a silent river of galaxies all flowing in the same direction at staggering speeds of millions of miles per hour. This isn't the local pull of the Great Attractor or the general expansion of space. This is a directional current on a scale so immense it seems to be sourced from a point beyond the edge of our observable universe. The observable universe is the sphere of space from which light has had time to reach us since the Big Bang, a cosmic horizon about 93 billion light-years across. The dark flow suggests that something unimaginably vast lying beyond that horizon is exerting a gravitational pull on everything inside it. It's as if we are living in a valley and have just discovered that all the rivers are flowing because of the gravitational tug of a mountain range so distant we cannot even see its peaks, a range that exists in a realm forever beyond our view. The evidence for this eerie motion comes from meticulous studies of the cosmic microwave background radiation, the ancient afterglow of the Big Bang that fills all of space. This radiation is not perfectly uniform. It contains tiny temperature variations, a fingerprint of the infant universe. As galaxy clusters move through space, they interact with this background radiation in a specific way known as the kinematic Sunyaev-Zeldovich effect. Essentially, the hot gas within these clusters scatters the microwave background photons, imprinting a very slight temperature shift that reveals the cluster's direction and velocity. When astronomers, led by Alexander Kashlinsky, analyzed the motion of over 1,000 clusters, they found a disturbing pattern. The clusters were all streaming toward a specific patch of sky between the constellations Centaurus and Vela, a motion that could not be explained by any known gravitational source within the observable universe. This was not a small, localized flow. It was a bulk flow, a coordinated movement of matter on a scale of billions of light-years. The gravitational pull required to cause such a vast, coherent stream would have to come from a structure of almost inconceivable mass, a concentration of matter so colossal it makes superclusters look like tiny specks by comparison. And the most unsettling part is that this colossal something is not on our map. It exists in the unobservable universe, its light and influence forever separated from us by the finite speed of light and the relentless expansion of space. This discovery, if confirmed, challenges one of the most fundamental principles in modern cosmology, the cosmological principle. This principle states that on the largest scales, the universe is homogeneous and isotropic, meaning it should look roughly the same in every direction and no place should be special. The cosmological principle is the foundation upon which we built our understanding of the Big Bang and cosmic evolution. The dark flow, however, suggests that on the very largest scales we can measure, the universe might not be uniform. It hints at a cosmic landscape that is fundamentally lopsided, with a grand underlying structure that extends far beyond what we can perceive. This opens the door to truly mind-bending possibilities. One of the most profound is the concept of the multiverse. In certain cosmological models, our Big Bang was not a unique event, but one of countless bubbles of spacetime inflating within a greater, multiversal foam. In this scenario, the dark flow could be the gravitational imprint of a neighboring universe bubble, a separate cosmos with its own distinct laws of physics, floating in a wider meta-reality. The structure pulling on our galaxy clusters would not be a supercluster, but an entire other universe, its gravity somehow leaking through the dimensional membrane that separates our realities. The thought that the motion of our entire observable cosmos could be influenced by the presence of a sibling universe is both awe-inspiring and deeply humbling, suggesting that everything we know is just a small province in an infinitely grander cosmic empire. Of course, such an extraordinary claim requires extraordinary evidence, and the dark flow remains a highly controversial topic within astronomy. Skeptics have proposed alternative explanations, suggesting that the observed signal could be a systematic error in how we interpret the cosmic microwave background data, or an effect of unknown local foregrounds contaminating the measurements. Subsequent studies have yielded conflicting results, with some supporting the original findings and others finding no evidence for a bulk flow on such large scales. This scientific debate is a healthy and necessary process, the mechanism by which we push the boundaries of knowledge and separate true cosmic revelations from potential illusions. Yet, the mere possibility that the dark flow is real carries a profound existential weight. It means our cosmic horizon is not a true boundary, but merely a limit of our perception. Beyond the veil of the observable universe, there lies a reality we can never directly see, but whose gravitational hand we might still feel. We are like sailors on a vast fog-bound ocean. We can map the currents and the winds, and we can see a certain distance in every direction. But we have just detected a persistent, powerful tide, a current that suggests the presence of a colossal landmass far beyond the fog bank, an unseen continent whose existence we can only infer from its pull on our own tiny vessel. Whether this unseen continent is a structure of unimaginable scale or an entirely separate universe, its potential existence redefines our place in the cosmos. We are not just inhabitants of a galaxy or a supercluster or even an observable universe. We may be citizens of a far larger and stranger reality, one whose full scope and nature are, for now, hidden in the dark. Leaving behind the unsettling currents of the dark flow, we journey toward a beacon of pure, unadulterated cosmic violence, a phenomenon so brilliant it can be seen from the edge of the observable universe, yet so destructive it threatens entire galactic ecosystems. This is the terrifying power of the quasar. Imagine a single object no larger than our solar system that can unleash more energy in 1 second than our Sun will produce in its entire 10 billion-year lifetime. A quasar can outshine a galaxy of 100 billion stars, blazing with the light of 1,000 Milky Ways from a point of near invisibility. This is not the gentle light of starlight, but the scream of matter being torn apart at the event horizon of a supermassive black hole, a cosmic engine of destruction that represents one of the most powerful and influential forces in the universe. At the heart of every quasar lies the ultimate predator, a supermassive black hole, often weighing billions of times the mass of our Sun. Unlike the dormant giant at the center of our own Milky Way, the black hole in a quasar is anything but quiet. It is a glutton, actively feeding on a staggering diet of gas, dust, and even entire stars. This material doesn't fall in directly. It forms a vast, flattened, revolving structure called an accretion disk, a cosmic whirlpool of superheated plasma spiraling inward at near light speed. Friction within this disk heats the material to temperatures of millions of degrees, causing it to glow with an intense, white-hot radiance across the entire electromagnetic spectrum. But this is only half the story. Perpendicular to this disk, focused by the black hole's immense magnetic fields, 2 jets of charged particles are launched at relativistic speeds, punching out across intergalactic space for hundreds of thousands of light years. These jets are the quasar's artillery, and they carry enough energy to sculpt the evolution of galaxies millions of light years away. The sheer power of a quasar is difficult to overstate. We are witnessing the conversion of matter into pure energy with an efficiency far beyond our most powerful nuclear reactors. Through the process of accretion, matter crossing the event horizon can convert up to 40% of its mass into energy, as dictated by Einstein's famous equation. This dwarfs the paltry 0.7% efficiency of hydrogen fusion that powers our Sun. This energy output is so immense that it can literally blow a galaxy apart from the inside out. The radiation pressure and powerful winds generated by the quasar can drive away the vast reservoirs of cold gas that are the raw materials for new star formation. This process, known as negative feedback, effectively sterilizes a galaxy, shutting down its stellar nurseries and turning it into a cosmic graveyard filled with aging, red stars and little potential for new life. The quasar becomes a self-limiting monster. Its very feast eventually cuts off its future food supply, often leading to its own eventual quieting. the presence of a quasar is a sign of a galaxy in its most violent and tumultuous phase, a brief, brilliant, and catastrophic adolescence. The influence of these cosmic engines, however, is not purely destructive. In a strange and paradoxical twist, quasars can also be agents of creation. Their relativistic jets, while capable of immense devastation, can also trigger star formation under the right conditions. When these high-energy jets slam into massive, slow-moving clouds of gas in intergalactic space or in the outer halos of galaxies, they create powerful shock waves. Think of it like a cosmic snowplow. The jet rams into the cloud, compressing the gas to incredible densities. This sudden compression can be the catalyst that pushes pockets of gas over the critical threshold needed for gravitational collapse, igniting a firestorm of new star birth in the wake of the jet's destructive path. This positive feedback means a quasar can simultaneously be extinguishing star formation in the inner regions of its host galaxy, while simultaneously lighting the fuse for stellar explosions in its distant outskirts. It is a dual nature of godlike power, holding the power of life and death over entire galactic ecosystems, a creator and a destroyer operating on scales that defy human comprehension. For us, situated in a quiet galactic suburb, the immediate threat from a quasar is thankfully minimal. The era of rampant quasars was in the distant past, when the universe was younger, denser, and galaxies were still forming. Most of the supermassive black holes in our cosmic neighborhood, including our own Sagittarius A star, are now in a quiescent state, having consumed the readily available fuel in their vicinity. The true terror of quasars is not that one might suddenly ignite nearby, but what they represent about the latent potential for violence slumbering at the heart of nearly every galaxy. Our own Milky Way has a 4 million solar mass black hole at its core. While it is quiet now, a major galactic merger or a sudden influx of gas could, in theory, reawaken this sleeping giant, turning the center of our galaxy into a brilliant, deadly beacon. This is a reminder that the calm, structured universe we see today is built upon a foundation of ancient, unimaginable violence. Quasars are the ghosts of that violent past, and a warning that the engines of creation are also, and perhaps always, the engines of ultimate destruction. Amidst the explosive deaths of stars and the silent pull of dark flows, there exists an end that is not violent but absolute. It is a fate not of fire but of ice, not of sound and fury but of perfect, unbreakable silence. This is the heat death of the universe, the ultimate victory of entropy, and the final, chilling destination for all that exists. To understand this profound and unsettling conclusion, we must first grasp a simple but powerful law of physics, the second law of thermodynamics. In essence, this law states that in any closed system, things tend to move from a state of order and concentration to a state of disorder and even distribution. Think of a hot cup of coffee left on a counter. It doesn't stay hot in one spot. The heat energy spreads out, warming the air around it until the coffee and the room are the same tepid temperature. The energy hasn't vanished, but it has become useless. It can no longer perform the work of heating your coffee because it is now everywhere at once. Now imagine applying this principle to the entire cosmos. The universe is the ultimate closed system. There is nothing outside of it to exchange energy with. And right now, it is a place of dramatic contrasts and incredible concentrations of energy. Stars like our Sun are monstrously hot fusion reactors, blazing against the near-absolute zero cold of the void. Galaxies are islands of intense activity in a sea of darkness. This represents a state of high energy concentration and therefore low entropy, but the second law dictates that this cannot last. Over trillions upon trillions of years, this cosmic gradient will inevitably flatten out. The timeline of this great cooling is almost too vast to comprehend, a countdown measured not in billions but in years with dozens of zeros. It begins with the quieting of the stars, one by one, across hundreds of billions of galaxies. the great fusion engines will sputter and die. The most massive stars will go first, ending their lives in spectacular supernova. Mid-sized stars like our Sun will swell into red giants, then collapse into cooling white dwarfs. The smallest, dimmest red dwarf stars, which are incredibly fuel efficient, will be the last to shine, glowing with a faint, deep red light for trillions of years. But eventually, even their fires will be extinguished. The last star in the universe will flicker out, and with it, the era of starlight will come to a permanent close. The cosmos will be plunged into a darkness deeper than any we can imagine, illuminated only by the occasional fading glow of stellar corpses. For a time, the universe will still hold pockets of activity. The dead stars, white dwarfs, neutron stars, and black holes will continue their silent orbits. Occasionally, the gravitational dance of these dark remnants will fling a planet from its system or cause two brown dwarfs to collide, creating a brief, final spark of light in the overwhelming dark. But even this chaotic motion is not eternal. Through a process known as gravitational radiation, the orbits of these dead objects will slowly decay. Binary systems will spiral inward and merge, and over staggering timeframes, even the intricate structure of galaxies themselves will evaporate. Stars will be flung out into the intergalactic void, while others will drift inward to be consumed by the supermassive black holes at the galactic cores. This leads to the next, even more eerie phase, the era of black holes. For an almost incomprehensible length of time, these gravitational monsters will be the sole dominant structures in the universe. They will continue to feed on the sparse, leftover gas and on the occasional star or planet that strays too close. But they, too, are not immortal. Through a quantum mechanical process at their very boundaries called Hawking radiation, black holes slowly leak their mass and energy back into the universe. It is an agonizingly slow drip for a supermassive black hole, but given enough time, even the largest will evaporate. One by one, they will pop out of existence in a final, faint burst of particles. When the last black hole vanishes, the universe will enter its final, true equilibrium. All matter will have decayed into its most stable, fundamental particles. Protons themselves, the building blocks of atomic nuclei, are predicted to decay over timescales so vast they make the age of the universe seem like a single heartbeat. What remains will be a thin, perfectly uniform soup of photons, neutrinos, electrons, and positrons, all spread out with an almost perfect evenness across an ever-expanding and now truly infinite emptiness. The temperature of this soup will approach absolute zero, the point where all molecular motion stops. In this state, no energy gradient exists anywhere. There can be no hot or cold, no here or there, no before or after in any meaningful sense. The universe will have reached a state of maximum entropy. It is a perfect, featureless, and eternal stillness. The true horror of the heat death is not the cold or the dark, but the absolute end of potential. In our universe today, energy can do work because it is concentrated. A star's heat can forge planets and power photosynthesis. The gravitational potential of a cloud of gas can collapse to birth new suns. But in the heat-dead universe, energy is everywhere, and therefore it is nowhere. It is like a battery that is completely, perfectly discharged. It holds a vast amount of total energy, but because that energy is spread evenly across an infinite volume, it cannot be harnessed to power any process, no matter how simple. No wind will blow, no clock will tick, no thought will be formed. The very concepts of time and change become meaningless. Physics itself reaches a state of permanent, unchangeable stasis. This is not an end that can be survived, outlasted, or reversed. It is the ultimate foreclosure on existence, a final, silent pronouncement that the universe has run its course and exhausted all possibilities. It is a fate written not in the fiery script of a supernova, but in the immutable, gentle, and utterly merciless logic of a fundamental physical law. Even as we contemplate the ultimate end of the cosmos, A more immediate and cyclical terror may be lurking in the outer darkness of our own solar system, a ghostly puppet master that has potentially orchestrated global catastrophes on our planet for hundreds of millions of years. This is the Nemesis hypothesis, a theory proposing that our Sun is not alone, but has a distant, dark companion. This hypothetical object, often envisioned as a dim red dwarf or a failed star known as a brown dwarf, is thought to follow a vast, elliptical orbit that takes it far beyond the known planets, out into the most remote and icy reaches of our solar system. Its gravitational influence, though faint, would be just enough to act as a celestial timer of doom. Once every 26 to 27 million years, as this dark star swings through its closest approach to the Sun, its gravity would stir up the frozen repository of our system's outer boundary, the Oort cloud. This immense spherical shell of trillions of icy bodies is the source of long-period comets, and a gravitational nudge from a passing nemesis could dislodge a cascade of these icy missiles, sending them on a slow, falling trajectory toward the inner solar system, turning our cosmic neighborhood into a shooting gallery with Earth as the prime target. The origins of this terrifying idea are rooted not in astronomy but in paleontology. In the 1980s, scientists analyzing the fossil record made a startling discovery. The history of life on Earth appears to be punctuated by mass extinction events that occur with a rough periodicity of about 26 million years. The most famous of these is the KT extinction that wiped out the dinosaurs 66 million years ago. But the fossil record suggests a rhythm of death, a recurring cycle where a significant percentage of life on the planet is suddenly erased. This pattern demanded an explanation that was both external to Earth and clock-like in its regularity. An extraterrestrial cause was the most logical candidate, but what could possibly act on such a precise multi-million-year timetable? Volcanic activity or climate change are not known to follow such a strict schedule. The Nemesis star was proposed as the perfect solution, a gravitational metronome orbiting our Sun, its predictable return triggering a predictable reign of destruction. The mechanism is chillingly elegant. The Oort cloud is a gravitationally delicate structure, a vast collection of icy planetesimals so far from the Sun that they are only loosely bound to our star. A passing star, or in this case a recurring companion, provides just the tiny gravitational perturbation needed to shake some of these icy bodies loose from their stable orbits. They begin their long fall sunward, and over thousands of years, a statistical number of them are bound to cross Earth's orbital path. A single impact from a large comet several miles across is all it would take to replicate the dinosaur-killing event, shrouding the planet in a dust cloud that blocks sunlight for years, collapses the food chain, and leads to a planetary die-off. But if such a deadly companion exists, why haven't we found it? The search for Nemesis has been one of the most challenging hunts in modern astronomy, precisely because of the nature of the proposed object. A brown dwarf, especially an old, cold one, emits very little light or heat. It would be a faint, cold ember against an already cold and dark backdrop, incredibly difficult to distinguish from the countless background stars. Its vast orbit means it spends most of its time at an immense distance, perhaps as far as 1 or 2 light-years away, a quarter of the distance to the nearest star, Proxima Centauri. At such a distance, its motion across the sky would be agonizingly slow, making it hard to detect through the traditional method of observing stellar movement. Astronomers have combed through data from powerful infrared sky surveys, like those conducted by NASA, a Wide-Field Infrared Survey Explorer, or WISE, which is specifically designed to detect the faint heat signatures of cool, nearby objects. These surveys have ruled out the existence of a large, Saturn-sized or Jupiter-sized object out to tremendous distances, and they have found no evidence of a star like a red dwarf within the proposed orbital range. However, the possibility of a very small, very cold brown dwarf, an object just a few times the mass of Jupiter that has cooled to temperatures comparable to Earth's, has not been entirely eliminated. It would be at the very limits of our detection capabilities, a true ghost in the machine of our solar system. The profound implication of the Nemesis hypothesis, even if it remains unproven, is the suggestion that our planet's habitability is not entirely under its own control. We may be living on a world whose long-term fate is periodically and arbitrarily reset by a gravitational puppet master we have never seen. It introduces a layer of cosmic fatalism to the history of life. The rise and fall of dominant species, from the trilobites of the ancient oceans to the great dinosaurs, may not be solely the result of terrestrial competition or gradual climate change, but could be influenced by the silent, rhythmic ticking of a celestial clock. The demise of the dinosaurs cleared the ecological stage for small, shrew-like mammals to eventually evolve into the astounding diversity of life we see today, including ourselves. In a very real sense, our own existence as a species could be a side effect of a previous extinction cycle triggered by this unseen companion. The thought that humanity's rise was made possible by a catastrophic event dictated by a dark star is a humbling and unsettling connection between our origins and a potential recurring celestial threat. While the hard evidence for Nemesis has dwindled, its legacy endures in a more generalized concept, the idea of periodic bombardment. Even if our Sun does not have a specific stellar companion, the solar system does move through the galaxy, and this grand journey itself may be the source of the cycle. As our Sun and its planets orbit the center of the Milky Way, they do not travel on a perfectly flat plane. They oscillate up and down, passing through the dense midplane of the galactic disk approximately every 30 to 35 million years. It is during these passages through this thicker region of stars and gas clouds that the Oort cloud could be perturbed not by one star, but by the combined gravitational influence of many passing stars and the gravitational tide of the galaxy itself. This galactic tide model provides an alternative, and perhaps more likely, mechanism for the SAME Chinese letter destruction without the need for a single dark companion. In this view, the entire galaxy becomes the timer, and our solar system's regular motion within it the trigger. The Nemesis star, therefore, transforms from a specific astronomical target into a powerful metaphor for the inherent vulnerability of our world to forces far beyond our immediate perception. It represents the ultimate hidden variable, a reminder that the most dangerous threats may not be the brilliant, explosive events we can see across the galaxy, but the dark, quiet, and patient objects moving silently in the vast, uncharted spaces of our own celestial backyard. Yet even the stable death of a star can mask a hidden, ferocious power, a dormant beast that, when stirred, unleashes a force so alien and potent it can redefine our understanding of magnetic fury. We now descend into the realm of the magnetar. Imagine the corpse of a massive star, a neutron star, already an almost impossibly dense object where a single sugar cube-sized piece of matter would weigh billions of tons. Now take that cosmic cinder and imbue it with a magnetic field of almost mythical strength. We are not talking about the simple pull of a fridge magnet or even the powerful field that protects our entire planet. The magnetic field of a magnetar is an entity in itself, 1 trillion times more powerful than Earth's and 1,000 times stronger than that of a typical neutron star. This is a level of magnetism so extreme that the laws of physics as we know them begin to warp and twist in its presence. In the vacuum of space near a magnetar, the magnetic field is so intense that it becomes a tangible thing. It would utterly dismantle matter itself from a staggering distance. If a human were to venture even within 1,000 miles of one, a proximity that is, needless to say, instantly fatal for many other reasons, the magnetic field would literally pull you apart. It would not just affect the iron in your blood, it would distort the very electron clouds that make up your atoms, tearing your molecular structure into a stream of subatomic particles. The common, chilling analogy is that a magnetar could erase the magnetic strip of every credit card on Earth from halfway across the galaxy, a distance of 20,000 light-years. But this parlor trick, as frightening as it sounds, is the least of its dangers. The true apocalyptic threat lies in what happens when this perfectly contained magnetic fury suddenly and violently releases its pent-up stress. This release comes in the form of a starquake. A neutron star has a solid, crystalline crust, an immensely hard surface layer floating on a superfluid core of neutrons. As the magnetar's immensely powerful magnetic field slowly evolves and stresses this crust, immense strain builds up, much like tectonic pressure building along a fault line on Earth. Eventually, the crust can no longer contain the stress. It cracks. This is a starquake, but to call it that is like comparing a firecracker to a nuclear bomb. The energy released in this single, catastrophic crustal shift is beyond comprehension. In a fraction of a second, a magnetar starquake can release more energy than our Sun will emit over its entire 10 billion-year lifespan. This energy does not emerge as a simple tremor. It is channeled directly into the magnetic field, which recoils in a colossal, explosive reconfiguration. This event unleashes a titanic flare of radiation, primarily in the form of gamma rays and X-rays, a burst of pure, lethal energy that shoots out across light years. We have witnessed this directly. On December 27, 2004, our solar system was bathed in a wave of radiation from a magnetar named SGR 1820, located 50,000 light-years away in the constellation Sagittarius. This object, for a mere 0.2 of a second, released a flash of gamma rays that was brighter than any other cosmic event ever recorded in our galaxy, outshining the full moon for that fleeting instant. It was so powerful that it actually compressed Earth's magnetosphere, the protective magnetic bubble that shields us from the solar wind, briefly ionizing the upper atmosphere to a level that disrupted long-range radio communications. If this magnetar had been located not 50,000 light-years away, but as close as 10 light-years, a stone's throw in galactic terms, the effects would have been catastrophic. The gamma-ray blast would have severely depleted our planet's ozone layer, potentially triggering a mass extinction event on par with the asteroid impact that wiped out the dinosaurs. The flash itself, though brief, would have been visible even in the daytime sky, a second sun appearing and vanishing in the blink of an eye, a silent herald of a biological collapse to come. What makes magnetars so especially unsettling is their unpredictability and their stealth. They are the dormant landmines of the cosmos. A magnetar does not announce its presence with a brilliant, continuous light like a quasar. It can sit quietly for thousands of years, an unremarkable point of light, its unimaginable power completely hidden, biding its time until its crust finally fractures. We only know they exist because we have been fortunate, or perhaps unfortunate enough to detect their occasional, violent outbursts from a safe distance. This leads to a deeply troubling question. How many of these magnetic monsters are lurking in our galactic neighborhood, unseen and unaccounted for? Astronomers estimate that roughly 1 in 10 supernova explosions creates a magnetar instead of a regular neutron star or black hole. Given the number of stars in the Milky Way, there could be tens of millions of these dormant magnetic ghosts scattered throughout the galaxy. Our solar system, as it travels along its galactic orbit, could potentially pass uncomfortably close to one without any prior warning. There is no way to survey them all. A quiescent magnetar is incredibly difficult to distinguish from an ordinary, faint star until the very moment it decides to tear its own crust apart. This transforms the galaxy from a collection of beautiful, distant points of light into a landscape that might be seeded with invisible, hyper-volatile traps. The magnetar is the ultimate embodiment of the phrase, "Still waters run deep." It is a stellar corpse that refuses to rest in peace, a remnant that holds within its core a coiled magnetic spring, waiting for the moment to unload a force of nature that can sterilize entire planetary systems from light years away. It is a reminder that in the cold, dark recesses of space, some of the most profound dangers are not the active, blazing monsters, but the silent, patient ones whose single bad day can echo across the galaxy. But after all these specific, violent threats, from magnetars to gamma-ray bursts, we are left with a more subtle, more philosophical terror, one that arises not from what we've found in the cosmos, but from what we haven't. This is the profound and deepening mystery framed by the Drake equation, a simple-looking formula that carries the weight of our deepest cosmic curiosity and our most profound existential fear. Conceived by astronomer Frank Drake in 1961, the equation was never intended to provide a single, definitive answer. Instead, it was a way to structure our thinking, to break down the vast, overwhelming question of "are we alone?" into a series of smaller, more manageable factors. It multiplies terms like the rate of star formation, the fraction of stars with planets, the number of planets that could support life, the fraction where life actually emerges, the fraction where that life becomes intelligent, the fraction that develops technology to communicate, and finally, the length of time such civilizations release detectable signals into space. Plug in optimistic numbers that life is common, intelligence is a natural progression, and civilizations are long-lived, and the galaxy should be a buzzing, vibrant network of countless societies. The equation seems to promise a crowded universe, yet when we point our most powerful radio telescopes to the sky, we are met with a silence so complete, so absolute, it seems to mock the equation's promise. This is the crushing weight of the great silence, the unsettling reality that forms the core of the Fermi Paradox. The universe presents us with two seemingly contradictory facts. The mathematics suggest a high probability for alien company, but the observational evidence delivers only a void. This discrepancy is one of the most important puzzles in all of science, and the solutions we are forced to consider are, almost without exception, terrifying. The true horror of the Drake equation lies in its final variable, L, the longevity of a communicative civilization. This is the factor over which we have no observational data, the great unknown that holds the key to the paradox. All the other terms, stars with planets, habitable worlds, even the origin of life, are becoming areas of active, fruitful research. We are finding exoplanets by the thousands, and our understanding of how life might begin is advancing. But L is different. It is not an astronomical or biological question. It is a sociological and technological one. It represents the lifetime of a species that has reached our current stage or beyond. And the silence of the cosmos suggests that this lifetime might, on average, be tragically, terrifyingly short. This leads us directly to the concept of the Great Filter, a hypothetical barrier so difficult to overcome that it prevents life from progressing to the stage of colonizing the galaxy. The terrifying question is where this filter is located. Is it in our past, meaning we are an incredible, one in a trillion fluke, or is it in our future, waiting for us just ahead? If the filter is behind us, if the jump from non-living chemistry to a self-replicating cell, or from simple cells to complex multicellular life, is the universe's true bottleneck, then we are a miracle. We are the winners of the most improbable lottery, and the silence is simply a reflection of our profound solitude. This is a comforting thought in one sense, as it means our future is open and unwritten. But it is also a deeply lonely one, placing the entire burden of consciousness and meaning onto our single, fragile world. The far more frightening possibility is that the Great Filter lies ahead of us. In this scenario, the development of life and even intelligence might be relatively common throughout the galaxy, but the development of a stable, long-lasting technological civilization is not. There may be a predictable, perhaps inevitable, point where a civilization gains the power to destroy itself, and with near certainty does so. We can see the potential pathways unfolding in our own society. It could be the ancient fear of nuclear annihilation, a war fought with weapons that can obliterate a biosphere in an afternoon. It could be a slower, more insidious demise through runaway climate change or ecological collapse, a failure of planetary stewardship. Or it could be a threat we are only now beginning to conceive, a catastrophe born from synthetic biology, where a genetically engineered pathogen escapes the lab, or from nanotechnology, where self-replicating machines reduce the entire planet to a gray goo. Perhaps the most discussed modern fear is the rise of a superintelligent artificial intelligence whose goals do not align with our survival. In this view, the cosmic silence is not a sign of our uniqueness but a graveyard. Every civilization that reaches our level of technological adolescence eventually discovers a technology that becomes its own tombstone. The stars are silent because no one survives their own technological puberty. The Drake equation in this light becomes a chilling mirror. We are plugging in the numbers as we develop, and the value of L we are desperately trying to calculate might, for nearly everyone, be tragically close to zero. Other explanations, while less focused on self-destruction, are equally chilling in their implications. There is the dark forest hypothesis, which imagines the galaxy as a vast dark woodland. In this forest, every civilization is a hidden hunter. Any civilization that reveals its location by broadcasting signals, as we do with SETI, is taking an enormous risk. A more advanced civilization detecting our signals might see us not as a potential friend, but as a potential competitor or threat, a sapling that could one day grow to challenge them for resources. The safest, most rational strategy in a dark forest is to remain absolutely silent, to listen intently, and to be prepared to preemptively strike down any other civilization you detect before it can do the same to you. In such a universe, the silence is not a sign of emptiness but of pervasive existential fear. No one is talking because everyone is hiding. Then there is the zoo hypothesis, which proposes that advanced civilizations are fully aware of us but have placed our solar system in a kind of cosmic quarantine or wildlife preserve. They observe us, perhaps waiting for us to reach a certain level of maturity or to overcome our own violent tendencies, but they strictly enforce a rule of non-interference. We are the exhibit and they are the silent curators. This idea is unsettling because it removes our agency, suggesting that our destiny is not fully our own and that we are being judged by standards we cannot comprehend. As we continue to search the skies with projects like the Breakthrough Listen initiative, which is scanning millions of stars across a wide range of frequencies, the continued silence is itself a powerful piece of data. It tells us that the universe does not contain a galaxy-spanning, communicative network of the kind we often imagine in science fiction. There are no open channels of interstellar diplomacy, no bustling trade routes between stars. The reality appears to be far quieter and far stranger. The Drake equation, therefore, evolves from a simple calculation into a profound philosophical tool. It forces us to look inward and confront the challenges of our own adolescence as a technological species. The period we are living in right now, where we possess the power to alter our planet and destroy our civilization, but have not yet developed the wisdom or the technology to reliably become a multi-planetary species, may be the most dangerous bottleneck in human history. It is the filter through which we must pass. The equation holds up a mirror to humanity, and the reflection we see is one of a species standing at a precipice, peering into a silent darkness, and wondering if that silence is the answer to the most important question we will ever ask. It suggests that the ultimate test may not be about finding others, but about surviving ourselves. As we've journeyed through colossal dangers and cosmic mysteries, it's easy to assume the greatest threats lie in the distant void or in the hearts of far-off galaxies. Yet one of the most unsettling puzzles in modern astronomy was discovered not in the depths of interstellar space, but right here in our own solar backyard, etched into the flight paths of two of humanity's most intrepid explorers. This is the strange and persistent riddle known as the Pioneer anomaly. Launched in the early 1970s, Pioneer 10 and Pioneer 11 were true trailblazers, the first spacecraft to travel through the asteroid belt, the first to make close-up observations of Jupiter and Saturn, and the first human-made objects placed on trajectories that would eventually carry them out of the solar system entirely. For decades, as they sailed farther and farther from the Sun, NASA's Deep Space Network meticulously tracked their positions using radio signals, creating a precise record of their velocity and location. And that's when engineers and physicists noticed something was subtly, yet undeniably, wrong. Both spacecraft were experiencing a tiny, unexpected, and constant deceleration. It was as if an invisible hand was gently but insistently applying the brakes, slowing the Pioneers down by a fraction of a nanometer per second squared. This may sound infinitesimally small, but over the course of a decade, that tiny drag added up to a deviation of thousands of kilometers from their predicted positions. For something designed with the precision of orbital mechanics, where trajectories are calculated with breathtaking accuracy, this was a glaring anomaly that simply could not be ignored. The immediate and most logical suspicion was that the spacecraft themselves were responsible. Perhaps it was a fuel leak, with minuscule amounts of propellant slowly venting from tiny cracks in the propulsion system, creating a tiny but constant thrust in the opposite direction of travel. Or maybe it was the gentle yet persistent pressure of the solar wind, the stream of charged particles flowing from the Sun, pushing back against the spacecraft. Yet, when engineers ran the numbers, these explanations fell short. The effect was too constant, too uniform, and it was observed on both spacecraft, even though they were traveling in nearly opposite directions. The most promising mundane explanation involved heat. The Pioneers were powered by radioisotope thermoelectric generators, which produced electricity from the decay of plutonium, and this process also generated a significant amount of waste heat. The theory was that this heat, radiating unevenly from the spacecraft bodies, could act like tiny photon rockets. If more heat was radiated from the back of the craft than the front, the photons carrying that thermal energy would impart a tiny recoil, effectively pushing the spacecraft backward and causing the observed deceleration. This was a compelling and perfectly physical explanation, one that resided firmly within the known laws of thermodynamics, but the mystery would not be so easily solved. For years, the thermal recoil theory remained just that, a theory. The complex geometry of the Pioneer spacecraft, with their heat sources, antenna dishes, and instrument booms, made it incredibly difficult to create a perfect thermal model that could account for every watt of power and confirm that heat radiation was the sole culprit. This lingering uncertainty opened the door for a far more thrilling and far more frightening possibility: that the anomaly was not an engineering quirk, but a sign that our understanding of gravity itself was flawed. Perhaps Newton's and Einstein's laws, which have so perfectly described everything from the fall of an apple to the orbit of Mercury, began to break down at the extremely weak gravitational fields found in the outer solar system. Some physicists proposed modifications to the law of gravity itself, tweaking Einstein's theory of general relativity to account for this tiny discrepancy. Such a modification would have revolutionary implications, potentially offering a new way to understand the universe without the need for dark matter. The idea that a fundamental pillar of physics might be showing its first crack in the quiet data streams from two aging probes was both electrifying and deeply unsettling. It suggested that the rules of the cosmos, which we assume are universal and constant, might in fact be more like local ordinances, changing as one moves into the darker, emptier realms of space. Beyond revised gravity, other exotic theories emerged from the shadows. Could the Pioneers be plowing through a diffuse, unseen halo of dark matter that clung to our solar system? This invisible, mysterious substance that dominates the mass of galaxies might also form a fine, gravitationally bound mist around our Sun, exerting an additional tiny drag on any object moving through it. While the density required would be extraordinarily low, the possibility was tantalizing, a hint that we could study dark matter not just in distant galaxies but right here at home. Even more speculative was the idea that the anomaly was a manifestation of higher dimensions, a subtle gravitational leak from a hidden dimension curled up within our own, its influence only becoming noticeable far from the dominant gravity of the Sun. For nearly 2 decades, the Pioneer anomaly festered as a low-grade fever in the body of physics, a persistent itch that mainstream science couldn't quite scratch. It was a classic ghost story, a tiny signal in the data, an unexplained whisper in the dark that challenged our deepest assumptions about how the universe works. The mystery finally began to unravel thanks to a Herculean effort of digital archaeology and sophisticated computer modeling. A dedicated team of researchers spent years recovering old data tapes, tracking down original project documents that had been stored in basements and warehouses, and piecing together a complete and accurate record of the spacecraft's telemetry over their entire operational lifetimes. They then built incredibly detailed thermal models of the Pioneer probes, accounting for every watt of electrical power generated and tracing how that power was consumed by the instruments and ultimately dissipated as heat from every surface of the complex spacecraft. This painstaking work revealed the truth, and it was both mundane and brilliant. The culprit was in fact heat, but it wasn't a simple case of thrust from thermal radiation. The analysis showed that the electrical power radiating from the spacecraft's central compartments was indeed uneven, a very slight but constant anisotropy in the heat flow, primarily from the heat emitted by the spacecraft's power sources being reflected off the back of their large main antenna dishes, produced just enough recoil to explain almost the entire anomalous deceleration. The invisible hand braking the Pioneers was not a flaw in gravity or a cloud of dark matter, but the gentle, predictable push of infrared photons, the same kind of heat you feel radiating from a warm oven. The case was finally closed, yet the legacy of the Pioneer anomaly is far more significant than its ultimate solution. It stands as a powerful testament to the importance of paying attention to the tiny details, the faint whispers in the data that don't quite fit. For 20 years, it was a glaring reminder of the potential for new physics lurking in our own cosmic neighborhood, a warning that our maps of reality are never truly complete. It demonstrated that even our most carefully planned missions into the unknown can bring back surprises we never anticipated, and that the most profound mysteries can sometimes be hidden in the tiniest of signals. The story serves as a humbling lesson. The universe is still full of secrets, and sometimes the scariest thing is not the answer we find, but the realization of how much we have yet to discover, even in our own celestial backyard. But what if death itself is not an absolute certainty, but a matter of perspective dictated by the bizarre rules of the quantum world? This brings us to one of the most unsettling thought experiments ever conceived, a mental exploration that merges quantum mechanics with a chilling form of existential horror. It's called the quantum suicide experiment, and it forces us to question not just the nature of reality, but the very continuity of our own consciousness. The setup is deceptively simple, rooted in the famous Schrödinger's cat paradox, but pushed to a deeply personal and terrifying extreme. Imagine a special device, a gun perhaps, aimed directly at you. This isn't a normal weapon, it's rigged to a quantum trigger. The trigger is tied to a single quantum event, like the decay of a radioactive atom. In any given second, the probability that the atom decays is 50%. If it decays, the gun fires. If it doesn't, it doesn't. According to the many worlds interpretation of quantum mechanics, every time this quantum coin is flipped, the universe splits. In one branch of reality, the atom decays and the gun fires. In the other branch, it does not, and you survive. Now, imagine this experiment is set to run once every second automatically for all eternity. From the perspective of an outside observer, this is a tragically short experiment. Within a few seconds, statistically, they would see you die. They would witness a version of you in which the quantum coin came up tails, and that would be the end of the story for them. But what is it like from your perspective as the conscious subject inside the box? The theory proposes something astonishing and deeply disturbing. You would never experience death. With each tick of the clock, the universe splits. In one branch you die, but in the other branch, a version of you remains conscious, perfectly aware, having just witnessed the trigger mechanism fail yet again. 1 second passes and you're still there. Another second passes and you're still there. From your first-person point of view, the experiment would seem to produce a miraculous, unbroken string of successes. You would experience an unending sequence of moments where, against all odds, the atoms simply refuse to decay. You would, in effect, subjectively experience immortality, not through magic or advanced technology, but through the simple, statistical fact that your conscious awareness can only continue in the branches of reality where you are still alive to have it. The sheer weirdness of this idea is difficult to overstate. It suggests that our continued existence might not be a robust physical fact, but a fragile, contingent outcome sustained by the very act of observation. We think we live in a single, objective timeline, but this experiment hints that our personal timeline is a thread weaving through an infinite tapestry of possibilities, automatically discarding every branch where our consciousness ceases. This isn't about having a lucky life. It's about the definition of life itself being tied to a specific quantum pathway. The terrifying implication is that for every near miss you've ever experienced in your life, every time you almost slipped and fell, every close call in traffic, there is another universe where a version of you was not so fortunate. And according to this hypothesis, you are simply the version of you that, through sheer quantum chance, has managed to stay on the winning path, oblivious to all the adjacent realities where your story ended prematurely. This transforms the universe from a place of deterministic cause and effect into a cosmic lottery where your sense of a continuous self is an illusion maintained by a perpetual, unconscious sorting mechanism. The world around you might feel solid and real, but this thought experiment suggests it is just the one slice of a vast multiverse that is compatible with your ongoing perception. The philosophical fallout from this is immense and deeply unsettling. It drags consciousness from the sidelines and places it at the very center of reality, or at least at the center of your reality. This idea is known as the anthropic principle applied to quantum mechanics. It's the notion that the universe we perceive must be compatible with our existence as observers. The quantum suicide experiment takes this to its logical, and some would say absurd, extreme. It proposes that conscious observation isn't just passive, it's actively selective. Your awareness effectively edits reality, pruning away the branches where you don't exist and leaving you only with the experiences of the timelines where you survive. This leads to a concept called quantum immortality, the notion that from a first-person perspective, you can never truly experience your own death. Even in a scenario where the odds of survival are astronomically low, like jumping from an airplane without a parachute, there would always be some bizarre, wildly improbable quantum fluctuation that saves you. Perhaps a sudden, impossibly powerful gust of wind cushions your fall, or the molecules in the ground momentarily phase apart as you hit. From the outside, everyone sees you die. But from your perspective, you would inexplicably survive, finding yourself in a world that seems to have defied physics just for you. Now, this is of course a thought experiment, and it is crucial to understand that it is not a prescription for how to live or a suggestion that you are invincible. The true horror lies not in the promise of immortality, but in the cold, alien picture it paints of existence. If this is true, then your loved ones, your friends, everyone you know, are not permanent fixtures in your reality. They are temporary companions on your particular quantum path. Every time someone you care about dies, from your perspective, they have effectively vanished from your timeline, while other versions of them continue in branches you can never access. This leads to a profound and lonely form of solipsism, where you are the only constant in a constantly shifting multiverse, and everyone else is a transient passenger. Furthermore, what does this imply about aging? Would you simply live on, experiencing an unending series of miraculous survivals, growing older and more decrepit, trapped in a body that should have failed countless times but somehow persists due to a never-ending sequence of quantum flukes? The prospect isn't one of vibrant eternal youth, but of a potential eternity of decay, where death remains an ever-present possibility in nearly all branches of reality. Yet your consciousness perpetually sidesteps it, landing you in the one reality where you continue no matter the cost. This is not a comforting vision of heaven, but a potential hell of infinite regress, where you are chained to a consciousness that can never truly end, forced to witness the unraveling of everything as you outlast stars, galaxies, and perhaps even the universe itself, always finding yourself in the one reality where conditions, against all odds, permit your continued solitary awareness. The quantum suicide experiment doesn't offer answers. It rips open a hole in our understanding of life and death, leaving us staring into a void of probabilistic chaos where the self is both eternal and utterly, terrifyingly alone. Just beyond the scattered realm of the Kuiper belt, far past the orbit of Neptune, the Sun's gravitational influence stretches to its absolute limit, encompassing a region of almost unimaginable scale and profound darkness. This is the Oort cloud, a theoretical shell of icy planetesimals that forms the true, outermost boundary of our solar system. Its existence was proposed by the Dutch astronomer Jan Oort to explain the origin of long-period comets, those rare, spectacular visitors that take thousands or even millions of years to complete a single orbit around the Sun. To grasp its sheer size is to challenge the limits of human comprehension. While the inner edge of this cloud may begin around 2,000 astronomical units from the Sun, 1 astronomical unit being the distance from Earth to the Sun, its outer fringe is thought to extend to a staggering 100,000 astronomical units. That is nearly halfway to the nearest star, Proxima Centauri. Picture our entire known planetary system, from Mercury to Pluto, as a tiny, gleaming marble. The Oort cloud would be a colossal, spherical fog bank surrounding it, stretching over a light year in radius. Within this unimaginable volume, trillions of icy objects are thought to drift in a deep, frozen slumber, each one a pristine relic from the solar system's violent birth, left over from the primordial disk of gas and dust that formed the planets. These are not compact, rocky asteroids, but fragile, dusty snowballs, often called dirty snowballs, composed of water ice, frozen gases like methane and ammonia, and rocky dust. They are the untouched building blocks of our cosmic neighborhood, preserved in the ultimate deep freeze for 4.5 billion years. The primary threat from this distant reservoir is not a constant bombardment, but the potential for a single, catastrophic disturbance. The Oort cloud is a gravitationally delicate structure. These icy bodies are so far from the Sun that they are only loosely bound to our star, their orbits easily perturbed by the slightest external nudge. The most common trigger is the gentle, persistent tug of the galactic tide. As our solar system orbits the center of the Milky Way, it bobs up and down through the plane of the galaxy. This movement creates a tidal force much weaker than the Moon's pull on Earth's oceans, but acting over immense timescales. This tide can slowly shake loose a cometary nucleus, sending it on a multi-million-year fall into the inner solar system. More dramatically, the occasional close pass of a nearby star can act like a gravitational plow, stirring up vast swaths of the cloud and potentially disloding a hail of icy missiles. When such an object is deflected inward, it becomes a long-period comet, a new visitor on a trajectory that can cross the orbits of the planets. The danger of a long-period comet is its unpredictability and its speed. Unlike asteroids, whose orbits are mostly within the ecliptic plane and can be mapped years in advance, these comets can approach from any direction, including from far above or below the plane of the solar system. They also travel at much higher velocities, often around 150,000 miles per hour or more, as they fall from the tremendous gravitational height of the Oort cloud. An impact from such an object would carry orders of magnitude more energy than an asteroid of the same size. The combination of a random approach vector and an immense closing speed could give us very little warning, perhaps only months or a few years, making deflection efforts nearly impossible with current technology. A direct hit would be an extinction-level event, replicating or exceeding the catastrophe that wiped out the dinosaurs, but with even less time to prepare. This ancient and familiar threat from our own solar system's backyard was suddenly joined by a new and even more enigmatic danger in October 2017, with the discovery of an object dubbed Oumuamua. This was not a local citizen of the Oort cloud. Telescopes on Hawaii detected a faint point of light moving at such a high speed that its trajectory could only be explained by one thing. It was an interstellar intruder, the first confirmed object from another star system to be observed passing through our own. Its name, from the Hawaiian for scout or messenger from afar arriving first, was perfectly chosen. Oumuamua was a herald, a proof that the space between stars is not entirely empty, but populated by wandering material ejected from other planetary systems. What made Oumuamua so deeply unsettling was its bizarre and unprecedented properties. It exhibited no visible coma or tail of gas and dust, the classic features of a comet. Yet, as it traveled away from the Sun, it experienced a tiny but measurable non-gravitational acceleration, as if something was gently pushing it. This is common for comets, as outgassing material acts like a small rocket engine, but no such gas was detected. Its shape, inferred from extreme variations in its brightness, suggested an object that was highly elongated, perhaps 10 times as long as it was wide, tumbling chaotically through space, a shape unlike any asteroid or comet seen before. The lack of outgassing and its strange shape led to a flurry of speculative explanations, including the fringe but provocative hypothesis that it could be a piece of alien technology like a light sail. While most scientists favor natural explanations, such as it being a fragment of a Pluto-like world from another system or a rare, purely rocky interstellar asteroid, the key point is that we simply do not know. Oumuamua represented a complete unknown in terms of composition, structure, and origin. It was a sample of another star system, and it passed within a mere 15 million miles of Earth, a cosmic hair's breadth. The profound implication of Oumuamua's visit is that our solar system is permeable to interstellar traffic, and not all of that traffic may be benign. If one such object was detected, there must be countless others, an invisible population of rogue asteroids, comets, and perhaps even dark, planet-sized bodies drifting through the interstellar void. The discovery of a second interstellar object, the Comet 2I/Borisov in 2019, which looked much more like a typical comet, confirms that this is a regular phenomenon. These interstellar interlopers pose a unique and frightening threat because they are complete wild cards. They can approach from any direction at virtually any speed and be composed of materials whose properties we cannot anticipate. An asteroid from our own belt has a certain known density and structural strength. An object forged in the crucible of an alien star system could be far denser or far more fragile, altering the impact effects in unpredictable ways. Its trajectory is not bound by the predictable clockwork of our solar system. It is a bullet fired from a distant, unknown source, and its path is a straight line through our neighborhood until the Sun's gravity slightly curves it. The warning time for such an object could be terrifyingly short. Unlike a long-period comet from our own Oort cloud, which still follows a predictable elliptical path, an interstellar object on a hyperbolic trajectory is just passing through. We might only detect it as it is already swinging around the Sun, giving us a matter of weeks or months before a potential impact if its path were to intersect with Earth. There is no way to map these objects in advance or predict their arrival. They are the ultimate celestial stealth bombers, dark and fast, revealing themselves only when they are already upon us. Together, the Oort cloud and interstellar intruders like Oumuamua paint a picture of a solar system that exists within a dynamic and occasionally hazardous environment. We are not isolated in a protective bubble. The gentle gravitational tides of the galaxy and the random passage of stars can stir the deep frozen relics of our own formation, sending them hurtling inward. Simultaneously, the galaxy itself sends its own projectiles across the void, remnants of planetary systems that formed, lived, and perhaps died around other stars. This dual threat represents a fundamental vulnerability. It means that a cataclysm can come not only from within our well-mapped local space, but from the truly unknown, the deep time of our own solar system's formation, or the entirely alien conditions of a world light years away. Our planetary defense efforts, which currently focus on cataloging near-Earth asteroids, are almost blind to these kinds of threats. Spotting a dark, inactive Oort cloud object or a fast-moving interstellar rock requires a new generation of wide-field survey telescopes like the upcoming Vera-C. Rubin Observatory, which will continuously scan the entire sky. Yet, even with advanced warning, the high speeds and unpredictable compositions of these objects would present a monumental challenge. They are reminders that our safe harbor is temporary, and that the quiet darkness beyond the planets is filled with drifting potential, both ancient and alien, waiting for the right gravitational nudge to bring it screaming into the light. And so we reach the end of our journey, a descent through 25 layers of cosmic dread that has taken us from the silent predators drifting between stars to the very laws of physics threatening to unravel. We began with rogue black holes, the invisible assassins capable of dismantling solar systems without warning, and witnessed the apocalyptic flash of gamma-ray bursts capable of sterilizing planets from across the galaxy. We felt the inexorable pull of the Great Attractor, guiding countless galaxies toward an unseen destination, and contemplated the ultimate void of the Boötes void, a sphere of emptiness so vast it defies comprehension. We grappled with the phantom grip of dark matter, the unseen king whose gravity sculpts the cosmos, and confronted the screaming silence of the Fermi Paradox, a haunting question mark over the potential for other life. We saw hypervelocity stars banished from their galactic homes forever and faced the ultimate dissolution of the Big Rip, where reality itself would be torn apart. We encountered the rhythmic death beams of pulsars and the looming cage of Kessler syndrome, a trap of our own making. We witnessed the slow-motion carnage of galactic cannibalism, the cryptic whisper of the Wow signal, and the slow, boiling death of our own sun. We felt the unsettling current of the dark flow, hinting at realities beyond our horizon, and stood before the raw power of quasars, the brilliant engines of galactic destruction and creation. We journeyed to the cold, final equilibrium of the universe's heat-death, the cyclical terror of the Nemesis hypothesis, and the coiled, magnetic fury of magnetars. We delved into the probabilistic horror of the quantum suicide thought experiment, the silent, icy threat of the Oort cloud, and the unnerving mystery of interstellar interlopers like Oumuamua. We even found a ghost in our own machine with the Pioneer anomaly, a tiny signal that challenged our grasp of physics itself. Each of these phenomena, from the galactic in scale to the quantum in nature, paints a consistent and humbling portrait of a cosmos that is profoundly indifferent to our existence. This is not a universe of gentle starlight and peaceful emptiness. It is a realm of ancient, violent forces and existential puzzles, where the conditions for life are a fragile and fleeting exception in a reality dominated by forces of unimaginable power and scale. The true terror is not necessarily that these things will harm us. The probabilities are often mercifully low, but the perspective they force upon us. We are temporary residents on a small rock, orbiting an average star in a quiet corner of a galaxy that is itself just one of trillions, all caught in a cosmic dance whose steps are dictated by mysteries we are only beginning to name. This journey through the dark is not meant to paralyze us with fear, but to ignite a deeper curiosity. It is a reminder that the unknown is not empty. It is filled with wonders that are as magnificent as they are terrifying, and that the pursuit of understanding them is one of the most noble and thrilling endeavors we can undertake. The universe is the ultimate story, and we have only just begun to read the first page. Now we turn this final thought over to you. After witnessing these 25 cosmic horrors, which one truly sent a shiver down your spine? Was it the silent, patient threat of the Great Filter, the idea that we might be alone because no one survives their own technology? Or was it the visceral, immediate dread of a magnetar starquake, capable of scouring a planet from light years away? Perhaps the philosophical chill of the heat death, the ultimate end of all possibility, resonated most deeply. Share your thoughts and your biggest cosmic fear in the comments below. We are genuinely curious to hear which mystery of the deep dark captured your imagination and your fear. And if you want to continue this exploration into the unknown, to unravel more of the universe's greatest secrets and terrifying truths, make sure to subscribe and hit the notification bell. Our journey into the shadows has only